Picture this: the Andromeda Galaxy is falling toward us. Right now, at this very moment, 2.5 million light-years away, our closest galactic neighbor is hurtling through the void of space on a collision course with the Milky Way. At 600,000 miles per hour, it speeds toward us, and yet it appears motionless in our night sky, frozen like a cosmic photograph, waiting. But here's what defies everything we thought we knew about galaxies, about gravity, about the very nature of cosmic motion itself. Andromeda shouldn't exist as we see it. Not in this form. Not with this structure. Not spinning the way it does, not organized the way it appears, not holding together against forces that should have torn it apart billions of years ago. Something at its center, something we cannot see, something that challenges our understanding of physics itself, is holding together 2 trillion stars in a dance we're only beginning to comprehend. What lies at the heart of Andromeda? What force, what mystery, what impossible phenomenon waits there in the darkness between stars? For centuries, we looked up at that faint smudge of light in the autumn sky and called it a nebula, a cloud, a minor feature of our own cosmic neighborhood. We were wrong. Spectacularly, magnificently wrong. The Andromeda Galaxy isn't just another collection of stars. It's a monster, a leviathan, a cosmic colossus that makes our own Milky Way look like a modest suburb in comparison. And at its core, at the very center of this spiral masterpiece, lies something so dense, so massive, so fundamentally strange that it warps the fabric of space and time itself into shapes our minds struggle to visualize. Imagine, if you will, a whirlpool in an ocean. Now imagine that whirlpool is 1 million light-years across. Imagine the water isn't water but stars, billions upon billions of them, each one a sun, each one potentially home to worlds we'll never see. Imagine that at the center of this whirlpool, instead of a simple drain, there exists a hole in reality itself, a place where the rules we've spent millennia discovering simply cease to apply. This is Andromeda. This is our destination. This is the journey we're about to take together, plunging through time and space toward the heart of something that shouldn't be possible, yet somehow is. The old astronomers, those patient watchers of the night who charted the heavens with nothing but their eyes and their determination, they saw Andromeda and called it fixed. The Persian astronomer Abd al-Rahman al-Sufi described it in 964 AD as a small cloud, never knowing he was looking at an island universe containing more stars than there are grains of sand on all of Earth's beaches combined. Charles Messier catalogued it as object number 31 in his famous list, M31, thinking it merely a fuzzy patch that might confuse comet hunters. Even the great William Herschel, who expanded our view of the cosmos beyond anything imagined before, believed these spiral nebulae were simply parts of our own stellar system, clouds of glowing gas within the Milky Way's boundaries. They were looking at something impossibly distant and seeing it as impossibly close. They were looking at a galaxy and seeing a cloud. They were looking at trillions of stars and seeing mist. But then came the photographs. Then came the spectroscopes. Then came Edwin Hubble, standing at the eyepiece of the Hooker telescope on Mount Wilson, documenting Cepheid variable stars in the Andromeda Nebula and realizing, with a mixture of terror and wonder that must have stolen his breath, that this object wasn't nearby at all. It was so far away that light itself, traveling at its cosmic speed limit of 186,282 miles per second, took millions of years to cross the gulf between Andromeda and Earth. In that moment, the universe expanded. Not physically, but in our minds, in our understanding, in our recognition of just how small we really are in the grand cosmic scheme. What Hubble saw through that telescope was revolutionary. But what he couldn't see, what no one could see, was what held Andromeda together. How could something so vast, so impossibly dispersed across such tremendous distances, maintain its shape? Why didn't it simply fly apart, its outer stars slinging away into intergalactic space as it rotated? The mathematics didn't work. The physics didn't make sense. The gravity of all those visible stars, even 2 trillion of them, wasn't enough to create the rotational pattern we observed. Think of it like this: imagine a carousel at a fairground, spinning around and around. The horses on the outer edge move faster than those near the center because they have farther to travel in each rotation. Now imagine that instead of horses, you have stars, and instead of a carousel, you have a galaxy. The stars on the outer edges of Andromeda should be moving much slower than those near the center, just like the horses on that carousel. But they're not. They're all moving at roughly the same speed, regardless of their distance from the core. It's as if there's some invisible mechanism, some hidden architecture, some dark scaffolding holding everything in place and accelerating the outer stars to speeds they shouldn't possess. This is where the old theories begin to crumble. This is where the comfortable certainties of Newtonian gravity start to show their cracks. This is where we're forced to confront the uncomfortable truth that what we can see might represent only a tiny fraction of what actually exists. Enter dark matter. Not a thing you can touch or see or detect directly, but something whose presence screams out from the mathematics, from the observations, from the stubborn refusal of galaxies like Andromeda to behave the way they should if only normal matter existed. Dark matter is the ghost in the cosmic machine, the invisible hand that shapes galaxies, the mysterious substance that outweighs everything we can see by a factor of 6 to 1. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we can measure. But it has mass, tremendous mass, and mass means gravity, and gravity means influence over the cosmic dance. Picture dark matter as a vast, invisible web surrounding Andromeda, permeating it, extending far beyond the visible edge of the galaxy into the darkness of intergalactic space. This web isn't made of atoms or particles as we understand them. It's something else, something that passes through ordinary matter like wind through a chain-link fence, yet whose gravitational embrace holds the entire galaxy in its grip. The stars we see, the gas clouds that glow in the light of newborn suns, the planets and the dust and the remnants of dead stars, all of it floats within this dark matter halo like flies trapped in an invisible sphere of amber. But even dark matter, as strange and mysterious as it is, doesn't fully explain what happens at the center of Andromeda. Because at the very heart of this galaxy, at the point around which everything else revolves, there exists something even more bizarre, even more challenging to our understanding of physics and reality. There, in a region smaller than our own solar system, compressed into a space that light itself would take only hours to cross, lies a mass equivalent to hundreds of millions of suns. This isn't a dense cluster of stars packed tightly together. This isn't a cloud of dark matter concentrated into a small volume. This is a supermassive black hole, a region where gravity has become so intense that it's literally torn a hole in the fabric of spacetime itself. How do we know it's there? We can't see it. By definition, a black hole is black, invisible, a void in the cosmos that swallows even light itself. But we can see its effects, oh yes, we can see what it does to everything around it. Stars near the center of Andromeda move at tremendous speeds, wheeling around an invisible point like planets around a sun, but much, much faster. These aren't the stately orbital velocities of stars in the galactic disk. These are frantic, desperate velocities, the speeds of objects caught in the grip of something massive beyond imagination. Measure the speeds of those stars. Calculate their orbital paths. Apply Kepler's laws of motion, refined over centuries of careful observation and mathematical development. The answer that emerges from the calculations is inescapable. Something with the mass of 100 million suns or more lurks at the exact center of Andromeda's rotation, invisible yet undeniable, present yet undetectable except through its gravitational influence. This is where our journey truly begins. Not at the outer edges of Andromeda, where the galaxy fades gradually into the darkness of intergalactic space, but right here, right now, as we contemplate what it would mean to travel to that center, to approach that supermassive black hole, to witness the cosmic violence and beauty that unfolds in the region where gravity becomes so strong that the normal rules of physics begin to break down. Imagine departing from Earth, leaving behind our pale blue dot, our familiar moon, our yellow sun that has nurtured life for billions of years. We accelerate, faster and faster, approaching speeds that would have been considered impossible just decades ago. The solar system falls away behind us. Mars recedes to a point of light, then disappears entirely. Jupiter's great bulk shrinks to a star, then to nothing. Neptune, Pluto, the Kuiper Belt objects tumbling in the distant darkness, all of them vanish as we push outward, toward the edge of the sun's domain and beyond. The stars that have always appeared fixed in the sky begin to shift their positions as we achieve velocities that would make light itself jealous. Ahead of us, Andromeda begins to grow. What started as a faint smudge of light no bigger than the moon in our sky starts to expand, to reveal its structure, to resolve into distinct features that no ground-based telescope can show. We can see the spiral arms now, glowing rivers of blue and white where new stars are being born in vast stellar nurseries. We can see the reddish glow of the central bulge, where older stars crowd together in numbers that dwarf anything we know from our own galactic neighborhood. Does it take millions of years to make this crossing? In real terms, yes it does. Light itself requires 2.5 million years to bridge the gap between the Milky Way and Andromeda. But this is a thought experiment, a journey of the mind as much as a journey through space, and in our imagination we can compress time, we can span distances, we can arrive at Andromeda's edge and begin our inward spiral toward its mysterious core. The outer reaches of Andromeda reveal a galaxy in motion, a galaxy alive with stellar evolution and cosmic recycling. Out here, where the spiral arms fade into the galactic halo, individual stars are separated by vast distances, light-years of emptiness between each point of light. These are the suburbs of Andromeda, the quiet zones where star formation has slowed or stopped entirely, where ancient stars have been drifting for billions of years, following their lazy orbits around the galactic center. But even here, in these seemingly empty regions, the evidence of dark matter surrounds us. Stars that should be barely bound to the galaxy, stars so far from the center that they should be on the verge of escaping into intergalactic space, move with surprising speed. Something holds them. Something keeps them circling. Something we cannot see exerts its invisible pull, maintaining the cohesion of this vast stellar assemblage. As we continue inward, the character of the galaxy changes. The spaces between stars shrink. The density of stellar populations increases. We begin to encounter more gas clouds, more regions where ultraviolet radiation from hot young stars causes hydrogen to glow with that characteristic deep red color. These are stellar nurseries, places where the raw material of stars, simple hydrogen and helium with traces of heavier elements, collapses under its own gravity to form new suns. The process of star formation is violent and beautiful in equal measure. Imagine a cloud of gas, tenuous beyond anything we experience on Earth, spread across light years of space. This cloud is cold, just a few degrees above absolute zero, and it's mostly hydrogen, the simplest and most abundant element in the universe. For millions of years, this cloud simply drifts, slowly rotating, gradually contracting under its own feeble gravity. Then something disturbs it. Perhaps a nearby star explodes in a supernova, sending a shock wave of matter and energy rippling through space. Perhaps the spiral density wave of Andromeda's rotating arm passes through, compressing the cloud. Whatever the trigger, the cloud begins to collapse more rapidly. Regions within the cloud that are slightly denser than their surroundings pull in more material. As they contract, they heat up. As they heat up, they spin faster, conserving angular momentum like a figure skater pulling in their arms. The center of each collapsing region becomes hotter, denser, more compressed. Pressure builds. Temperature rises. The atoms collide with increasing violence, moving faster and faster as thermal energy increases. And then, when the temperature at the core reaches 10 million degrees, something magical happens. Hydrogen nuclei, normally repelled by their mutual positive charges, slam together with such force that they overcome the electromagnetic repulsion and fuse, combining to form helium and releasing tremendous amounts of energy in the process. A star is born. Light explodes outward from the core, pushing back against the infalling matter, creating an equilibrium between gravity trying to crush the star and radiation pressure trying to blow it apart. This balance will continue for millions or billions of years, depending on the star's mass, providing a steady source of light and heat to the surrounding space. We pass through region after region where this drama plays out. Young blue stars, massive and bright, burn through their fuel at prodigious rates, living fast and dying young in cosmic terms. Smaller yellow stars like our Sun burn more conservatively, promising lifespans measured in billions of years. And everywhere, the spiral structure of Andromeda reveals itself more clearly, those grand sweeping arms where stars and gas concentrate as they orbit the galactic center. Why does Andromeda have a spiral structure? Why do so many galaxies organize themselves into these beautiful, rotating pinwheels? The answer lies in density waves, in the way gravity can create patterns in rotating systems. Think of traffic on a circular highway. Even if all the cars are moving at slightly different speeds, there will be regions where cars bunch up, where traffic moves more slowly, where the density of vehicles increases. These congestion zones rotate around the highway, but they're not made of specific cars. The cars pass through the congested regions and emerge on the other side. The pattern persists even though the individual vehicles change. Andromeda's spiral arms work the same way. They're not permanent structures made of specific stars. They're density waves, regions where stars and gas temporarily crowd together as they orbit. Stars enter the spiral arm from behind, slow down slightly due to the increased gravitational pull of all that concentrated mass, then accelerate out the other side. The spiral pattern remains, even though the stars constantly change. It's a pattern in motion, a wave in a sea of stars, rotating slowly around the galactic center at a rate different from the stars themselves. But the spiral arms aren't just aesthetic features, aren't just pretty patterns that make galaxies photogenic. They're crucial to star formation, to the ongoing evolution of the galaxy. When gas clouds enter a spiral arm, they're compressed by the increased density. This compression can trigger collapse, can initiate the process of star formation we described earlier. That's why the spiral arms glow so brightly in blue light, the light of hot young stars. That's why we see those red nebulae of glowing hydrogen marking the spots where stars are being born even now, 2.5 million years ago by Earth's calendar, but right now in our journey through Andromeda's structure. As we spiral inward, following one of these great stellar rivers, we notice the stellar population changing. The stars become older on average. There are fewer of those bright blue young stars and more yellow and orange stars, middle-aged suns that have been burning steadily for billions of years. The gas clouds thin out. Star formation slows. We're entering the transition zone between Andromeda's disk and its bulge, between the flat spiral structure and the ellipsoidal core. The galactic bulge is a different world, a different environment entirely from the disk we've been traversing. Here, stars pack together much more densely. The spaces between them shrink from light years to mere light months or even light weeks. If a planet orbited a star in this region, its night sky would be magnificent beyond description, filled with thousands of stars bright enough to cast shadows, a permanent twilight created by the glow of countless suns. But that crowding comes at a cost. Stars in the bulge follow chaotic orbits, not the orderly circular paths we see in the disk. They plunge in toward the center, swing back out to the edges of the bulge, dive down below the galactic plane and back up above it. Their motion is three-dimensional and random, creating a swarm rather than a smooth flow. This randomness is crucial to understanding how the bulge maintains its shape. In the disk, angular momentum, the tendency of rotating things to keep rotating, maintains the flat structure. In the bulge, it's random motion, stars flying in all directions, that creates pressure against gravity, preventing collapse. Think of it like the difference between a merry-go-round and a swarm of bees. The merry-go-round rotates in a plane, all the horses moving together in an organized, predictable way. The bees buzz in all directions, up and down and sideways, apparently chaotic yet maintaining a coherent swarm. The disk is the merry-go-round. The bulge is the bee swarm. We're getting closer now. Closer to the center. Closer to the mystery. The stellar density continues to increase as we approach the absolute core of Andromeda. Stars here are ancient, formed in the early days of the galaxy when the universe itself was younger, when the first generations of stars had just begun to enrich the cosmos with heavy elements created in their nuclear furnaces and scattered by their supernova deaths. These old stars tell a story, a history written in their chemistry and their motion. By analyzing their light, by breaking it down into its component wavelengths with spectroscopes, we can read the abundance of elements heavier than helium. These metals, as astronomers call them, using a definition that would make a chemist weep, were not present in the early universe. The Big Bang created hydrogen and helium with traces of lithium, and that was it. Everything else, every atom of carbon in our bodies, every oxygen molecule we breathe, every iron atom in our blood, was forged in the hearts of stars and scattered across space when those stars died. Stars in Andromeda's central bulge show relatively low metal content compared to younger stars in the disk. This confirms their age, confirms that they formed when the galaxy was young, before countless generations of stars had lived and died and enriched the interstellar medium with their nuclear products. These are the elders of the galaxy, the ancient ones who have witnessed billions of years of cosmic evolution. And they're moving fast. Incredibly fast. As we approach within a few hundred light-years of Andromeda's absolute center, the orbital velocities of stars become extraordinary. Hundreds of kilometers per second. thousands of kilometers per second. Speeds that would carry a star from Earth to the Sun in hours, speeds that speak of tremendous gravitational forces, speeds that can only mean one thing: we're approaching something massive beyond comprehension. The center itself, when we finally reach it, doesn't look particularly spectacular at first glance. There's no beacon marking the galactic core, no sign saying, "Center of galaxy, mass of supermassive black hole, 100 million suns." It's just more stars, more densely packed than anywhere else, swarming like moths around a flame we cannot see. But the evidence is there in their motion, in the fury of their orbits, in the way they wheel and dance around a central point. What is a black hole? The question seems simple, but the answer challenges every intuition we have about the universe. A black hole is what happens when matter becomes so compressed, so dense, that its gravity becomes overwhelming. At a certain critical density, the escape velocity from an object's surface exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. Not matter. Not radiation. Not even information itself, at least according to classical physics. The boundary between inside and outside, the point of no return, is called the event horizon. It's not a physical surface. There's nothing there, no membrane, no barrier you could touch. It's simply the point where the escape velocity equals light speed. Cross the event horizon traveling inward, and you can never come back. Every direction points deeper into the black hole. The future direction in spacetime, the direction we call forward in time, now points toward the singularity at the black hole's center. You cannot avoid it any more than you can avoid tomorrow. Your fate is sealed from the moment you cross that invisible boundary. What lies beyond the event horizon? What happens at the singularity where all the black hole's mass is concentrated? We don't know. We can't know, not without a theory of quantum gravity that successfully marries Einstein's general relativity with quantum mechanics. Our best theories, tested and refined over a century of observations and experiments, break down completely at the singularity. Infinities appear in the equations, signal flags that our mathematics has reached the limit of its applicability, that we're asking questions about a regime where the physics we know simply doesn't apply. But we can observe what happens near the event horizon, in the region where spacetime is severely warped but not yet completely disconnected from the outside universe. And what we see is both terrible and magnificent. Matter falling toward a black hole doesn't simply plunge straight in. It has angular momentum, that tendency to keep rotating that we've mentioned before. As it falls, it speeds up, conserving angular momentum by spinning faster as it gets closer to the center, just like that figure skater we mentioned earlier. This creates an accretion disk, a whirling maelstrom of gas and dust spiraling inward toward its doom. The accretion disk is hot. Incredibly hot. As material falls inward, gravitational potential energy converts to kinetic energy, the energy of motion. Particles collide with tremendous violence. Friction between different parts of the disk, moving at slightly different velocities, generates heat. Temperatures soar to millions of degrees. At these temperatures, the gas emits X-rays, high-energy photons that stream outward from the accretion disk, providing one of our best ways to detect black holes. But the supermassive black hole at Andromeda's center isn't actively feeding right now. At least not on the scale that some black holes do. We don't see the brilliant glow of a quasar, that luminous beacon created when a supermassive black hole devours enormous quantities of matter and outshines its entire host galaxy in the process. Andromeda's core is relatively quiet, relatively sedate. The black hole is there, lurking in the darkness, but it's not currently consuming matter at a prodigious rate. This raises fascinating questions. Do supermassive black holes turn on and off? Do they have active periods and quiet periods? The evidence suggests yes. A quasar isn't a different kind of object from a normal galaxy. It's the same thing, just viewed during a phase when the central black hole is actively feeding. If we could watch Andromeda for billions of years, we might see it flare up, might see it go through a quasar phase when some large influx of matter spirals into the central black hole and creates a blaze of radiation that outshines all 2 trillion stars combined. What would it be like to orbit close to Andromeda's central black hole? The experience would be profoundly strange, challenging every assumption we make about the nature of space and time. Einstein's general relativity tells us that gravity isn't a force in the traditional sense. It's a curvature of spacetime itself. Mass and energy warp the fabric of the universe, creating curves and valleys in the geometric structure of reality. Objects moving through this curved spacetime follow paths we interpret as orbital motion, but from the object's perspective, it's moving in a straight line through curved space. Near a supermassive black hole, the curvature becomes extreme. Spacetime is warped into shapes that defy visualization. If you were in a spacecraft orbiting close to the event horizon, you would experience several bizarre phenomena. First, time itself would slow down relative to the outside universe. Clocks on your spacecraft would tick normally from your perspective, but if you could observe clocks farther from the black hole, you would see them running faster. If you orbited there for what felt like an hour and then returned to the outer regions of Andromeda, you might find that years or decades had passed for the rest of the universe. This time dilation effect is real, measurable, and confirmed by countless experiments in our own solar system and on Earth itself. GPS satellites have to correct for time dilation both from their velocity and from being higher in Earth's gravitational well, or they would quickly become useless for navigation. Near a black hole, the effect becomes extreme. Light itself behaves strangely near a black hole. Photons emitted from the accretion disk can orbit the black hole multiple times before either falling in or escaping outward. This creates optical illusions, regions where you might see multiple images of the same star, bent and distorted by the black hole's gravitational lensing effect. The black hole itself would appear as a dark circle, blacker than the space around it because it's literally a hole in spacetime, but surrounded by a thin ring of light, photons from the accretion disk that manage to escape at the last possible moment. But perhaps the most disturbing effect would be tidal forces, the difference in gravitational pull between the near side and far side of an object. On Earth, tidal forces from the moon create our ocean tides, pulling the water on the near side toward the moon and allowing the water on the far side to bulge outward. Near a black hole, tidal forces become monstrous. If you fell feet first toward a black hole, the pull on your feet would be enormously stronger than the pull on your head. You would be stretched, elongated, spaghettified in the grim terminology astronomers use. Long before you reached the event horizon, tidal forces would rip your body apart, atom by atom, reducing you to a stream of subatomic particles. For a supermassive black hole like the one at Andromeda's center, though, something counterintuitive happens. The event horizon is so far from the singularity that tidal forces at the horizon itself might actually be survivable, at least momentarily. The black hole is so large that the difference in gravitational pull from one side of your body to the other wouldn't be instantly fatal. You might actually cross the event horizon and survive for a brief period before the inevitable tidal forces closer to the singularity destroyed you. Not that it would help. Once across that boundary, there's no return. The entire observable universe would appear compressed into a bright circle behind you, blue-shifted and growing smaller. Ahead, in the direction of the singularity, there would be only darkness, the ultimate darkness of the unknown. Your subjective experience of time would continue normally, but from the outside universe's perspective, you would appear frozen at the event horizon, your image redshifted and dimmed until you vanished from view entirely. You would have left the universe as far as outside observers were concerned, passed beyond the veil into a realm from which no information returns. But let's step back from this nightmare scenario and consider what the existence of this supermassive black hole tells us about galaxy formation, about cosmic evolution, about the relationship between these monstrous objects and the galaxies that host them. Here's a remarkable fact: essentially every large galaxy appears to contain a supermassive black hole at its center. The Milky Way has about 4 million solar masses, which we've observed by tracking stars orbiting it at the galaxy's core. Andromeda has perhaps 100 million solar masses or more. Some galaxies have even larger ones, billions of solar masses, black holes so massive that their event horizons span distances larger than our entire solar system. How did these monsters form? We don't fully know, and that uncertainty, that gap in our understanding, represents one of the most intriguing puzzles in modern astrophysics. Several theories compete, each with its strengths and weaknesses. Perhaps supermassive black holes formed directly in the early universe, condensing from enormous clouds of gas without ever going through a stellar phase. Perhaps they started as normal stellar mass black holes, formed from the deaths of massive stars, and then grew by consuming matter and merging with other black holes. Perhaps they formed through some exotic mechanism we haven't even imagined yet, some process that only occurred in the unique conditions of the early universe. What we do know is that there appears to be a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the velocity dispersion of stars in the galactic bulge. This relationship, discovered through painstaking observations of many galaxies, suggests that black holes and galaxies co-evolve, that they influence each other's growth and development in ways we're only beginning to understand. Think about that for a moment. The black hole at Andromeda's center, despite containing perhaps 100 million solar masses, represents less than 1% of the galaxy's total mass. It's tiny compared to the galaxy as a whole. And yet its presence has shaped the galaxy's evolution, influenced how stars form and move, affected the distribution of matter across hundreds of thousands of light-years. How can something so relatively small have such disproportionate influence? The answer might lie in the black hole's active phases, those periods we mentioned earlier when it voraciously consumes matter and blazes with energy. During these phases, the black hole doesn't just emit light. It also generates powerful jets, streams of matter and energy that rocket outward from near the event horizon at speeds approaching light speed. These jets can be millions of light-years long, extending far beyond the galaxy itself. They plow through the intergalactic medium, creating shock waves, heating gas, potentially preventing that gas from falling into the galaxy and forming new stars. This might be the key to understanding the black hole's influence. By periodically turning on and blasting energy into its surroundings, the supermassive black hole regulates star formation in the galaxy, preventing runaway growth, maintaining a balance between matter falling into the galaxy and matter being prevented from forming stars. It's a cosmic thermostat, keeping the galaxy in a stable configuration. Or perhaps the relationship is even deeper. Perhaps black holes and galaxies don't just co-evolve but are fundamentally linked in ways we haven't discovered. Perhaps understanding one requires understanding the other. Perhaps the question, how did supermassive black holes form, cannot be answered separately from the question, how did galaxies form? These are the kinds of questions that keep astrophysicists awake at night, staring at computer screens filled with data, running simulations that span billions of years of cosmic evolution, trying to understand the dance between matter and gravity and energy that has shaped the universe we observe. But let's zoom out again. Let's pull back from the immediate vicinity of the black hole and consider the central region of Andromeda as a whole. Because something else remarkable lurks here, something we haven't discussed yet. Andromeda's core is double. Not in the sense of having two black holes, though some galaxies do possess binary supermassive black holes, but in the sense that the densest concentration of stars is offset from the dynamical center, from the point around which everything orbits. Why would this be? Why wouldn't the densest part of the galaxy sit exactly at the center? The answer, as best we can determine, relates to Andromeda's history, to its violent past of mergers and collisions with other galaxies. Andromeda didn't form in isolation. It grew, consuming smaller galaxies, stripping stars from neighboring systems, gradually accumulating matter and mass over billions of years. Each merger disturbed the galaxy's structure, sent ripples through the stellar population, potentially displaced the densest concentration of stars from the exact center. Evidence of these past collisions surrounds us as we orbit in the central regions. Stellar streams, long arcs of stars with similar motions and compositions, curve through Andromeda's halo like cosmic contrails. These are the remnants of smaller galaxies that Andromeda consumed, satellite galaxies that ventured too close and were torn apart by tidal forces, their stars scattered into long streams that continue to orbit through the larger galaxy. It's a violent history, a story of cannibalism and destruction played out over cosmic timescales. And it's not over. Andromeda is still consuming satellite galaxies. We can see several of them now, small elliptical galaxies orbiting Andromeda's outskirts, gradually being pulled closer, gradually being distorted by tidal forces, destined to eventually merge with the larger galaxy and add their matter to Andromeda's mass. And then there's the big one. The collision that's coming. The merger between Andromeda and the Milky Way. Remember how we started this journey? With the shocking fact that Andromeda is falling toward us, accelerating across the intergalactic gulf, destined to collide with our own galaxy in approximately 4 billion years. This isn't speculation. This isn't uncertain. The velocities have been measured. The trajectories have been calculated. The outcome is inevitable. What will happen when two such massive galaxies collide? Not what you might imagine. Despite containing trillions of stars between them, the galaxies are mostly empty space. The distances between stars are so vast that the likelihood of actual stellar collisions during the merger is negligible. Stars from the Milky Way and stars from Andromeda will pass between each other like two clouds of gnats merging, individual insects flying past each other without touching. But gravitational interactions will be profound. Stars will be flung into new orbits. The spiral structures of both galaxies will be destroyed, disrupted by the gravitational chaos. Gas clouds will collide, and unlike stars, gas clouds can't pass through each other. They'll compress, shock, heat, and trigger enormous bursts of star formation. The merged galaxy, sometimes called Milkomeda in a fit of creative naming, will blaze with the light of billions of newly born stars. And the central black holes, those supermassive singularities at the core of each galaxy, will eventually merge as well. They'll spiral toward each other, drawn together by gravity, orbiting faster and faster as they approach. In the final moments before merger, they'll emit gravitational waves, ripples in spacetime itself, carrying away energy and angular momentum. And then they'll coalesce into a single, even more massive black hole, the combined mass of both objects creating a new monster at the heart of the merged galaxy. This is the fate written in the stars, the destiny that awaits our galaxy and Andromeda both. Not in our lifetimes. Not in the lifetime of our species, if we survive that long. Not even in the lifetime of our sun, which will have swelled into a red giant and engulfed Earth long before the galaxies merge. But it will happen. The universe cares nothing for human timescales, operates according to rhythms measured in billions of years. Standing here, metaphorically speaking, at the center of Andromeda, contemplating its supermassive black hole, considering its history and its future, one cannot help but feel a sense of cosmic perspective. We humans, evolved on a small planet orbiting an average star in the outer suburbs of an unremarkable galaxy, have managed to understand something of the universe's grand architecture. We've pieced together the story of galaxy formation from scattered clues. We've detected invisible matter through its gravitational effects. We've inferred the existence of objects so bizarre that they seem like science fiction, yet they're real, they're out there, they're shaping the cosmos on the largest scales. How did we accomplish this? How did creatures who evolved to hunt and gather on African savannas develop the capacity to comprehend black holes and galaxy collisions and the warping of spacetime? The answer lies in one of the most remarkable features of the universe: it follows rules. It operates according to physical laws that apply everywhere, at all times. Gravity on Earth works the same way as gravity in Andromeda. Light travels at the same speed here as it does 2.5 million light-years away. The mathematical relationships we discover in our laboratories remain valid across the entire observable universe. This universality of physical law is not something we could have predicted in advance. The universe didn't have to be comprehensible. It could have been chaotic, random, governed by different rules in different places or at different times. But it isn't. And that single fact, more than anything else, has enabled our understanding, has allowed us to extrapolate from experiments on Earth to the centers of distant galaxies, to take measurements in our solar system and apply them across cosmic distances and timescales. Yet for all our knowledge, for all our understanding, mysteries remain. Dark matter is still dark, its fundamental nature unknown despite decades of searching. We don't know what it's made of, why it interacts so weakly with normal matter, whether it's a single type of particle or multiple kinds with different properties. We simply know it's there, inferred from its gravitational effects, essential to explaining why galaxies hold together and why the universe has the large-scale structure we observe. Dark energy is even more mysterious. This is the name we give to whatever is causing the universe's expansion to accelerate, driving galaxies apart at ever-increasing speeds. It represents roughly 70% of the total energy content of the universe, yet we have no idea what it is. Some proposals suggest it's a property of space itself, a cosmological constant as Einstein once proposed and then retracted. Others suggest it's a new kind of field or particle. Still others wonder if it indicates that our understanding of gravity breaks down on the largest scales. We don't know. We're mystified by the dominant component of the universe. And then there are the deepest mysteries, the questions that might not even have answers in any conventional sense. What happened before the Big Bang? What lies beyond the edge of the observable universe? Is our universe unique or one of many in some vast multiverse? What is the ultimate fate of the cosmos? These questions take us beyond the realm of current science into the realm of speculation and philosophy. We can make educated guesses, can follow our theories to their logical conclusions, can imagine scenarios that might be consistent with physics as we understand it. But we can't know. Not yet. Perhaps not ever. The center of Andromeda, this place we've been exploring in our imagination, this region of extreme gravity and ancient stars and hidden singularities, represents both the pinnacle of our understanding and the limits of our knowledge. We can describe what's here. We can measure and calculate and model. We can explain how it formed and predict how it will evolve. But the deepest questions, the why questions rather than the how questions, remain tantalizingly out of reach. Why does anything exist rather than nothing? Why do the laws of physics have the particular forms they do? Why is the universe comprehensible to creatures like us? These are not scientific questions in the traditional sense because we can't design experiments to answer them. They're philosophical questions, perhaps even theological ones, depending on one's perspective. Yet they arise naturally from our contemplation of the cosmos. Standing here, gazing metaphorically into the darkness of a supermassive black hole at the heart of a galaxy 2.5 million light-years from Earth, one cannot help but wonder about meaning, about purpose, about whether the universe is simply a collection of particles and forces or whether there's something more, something we're missing, some deeper layer of reality that we haven't yet glimpsed. The history of science suggests humility is warranted. Time and again, we've thought we understood the universe, only to have new discoveries overturn our assumptions. The Earth wasn't the center of the solar system. The solar system wasn't the center of the universe. Our galaxy wasn't the universe. The universe wasn't static and eternal. Each expansion of knowledge revealed our previous worldview as too small, too limited, too Earth-centric or human-centric. What will the next revolution reveal? What assumptions that we currently hold dear will future generations look back on and smile at, the way we smile at the notion of crystalline spheres carrying the planets around Earth? We cannot know. We can only continue to observe, to measure, to question, to push against the boundaries of our understanding and see where they give way. The journey to the center of Andromeda, in this sense, is really a journey into ourselves, into the human capacity for wonder and understanding. The black hole we've been contemplating isn't just a physical object 2.5 million light-years away. It's a challenge to our comprehension, a test of our theories, a reminder of how much we've learned and how much we have yet to learn. Every photon that reaches our telescopes from Andromeda's core left that galaxy millions of years before humans existed. It crossed the intergalactic void while our ancestors were still single-celled organisms in ancient oceans. It traveled through space while continents formed and separated, while ice ages came and went, while life evolved and diversified and eventually produced creatures capable of capturing that photon and extracting information from it. That photon carries a message, encoded in its wavelength and intensity and polarization. It tells us about the conditions in Andromeda's core at the moment of its emission. It provides data we can analyze, interpret, incorporate into our models of how galaxies work. It's a time machine, allowing us to see into the past, to observe the universe not as it is now but as it was millions of years ago. And yet that same photon, that same quantum of electromagnetic energy, also carries a reminder of the universe's vastness, of the cosmic scales involved, of how tiny and brief our existence is compared to the life cycles of galaxies and stars. We are patterns in the universe that have become complex enough to contemplate the universe itself. We are stardust that has gained consciousness and looks back at the stars. We are the universe thinking about itself. This is perhaps the most profound realization we can draw from our journey to Andromeda's center. We are not separate from the cosmos, not observers standing outside looking in. We are part of it, made of the same matter, following the same laws, composed of atoms forged in stellar furnaces and scattered across space by supernova explosions. The iron in our blood, the calcium in our bones, the carbon that forms the basis of our biochemistry, all of it was created in stars, perhaps stars in the Milky Way, perhaps even stars in Andromeda whose light will never reach Earth before our galaxy and Andromeda merge. We are connected to the universe in the most literal, physical sense. We are cosmic phenomena, as surely as stars and galaxies and black holes are cosmic phenomena. Our thoughts, our dreams, our understanding, these are all manifestations of the universe's complexity, examples of what matter can do when organized in particular ways. Does this make the universe meaningful? Does the existence of consciousness, of understanding, of beings capable of contemplating black holes and calculating galaxy mergers, imbue the cosmos with purpose? Or are we simply elaborate patterns, temporary local decreases in entropy destined to fade away when the stars die and the universe grows cold and dark in the unimaginably distant future? These questions have no definitive answers. They depend on what we mean by meaning, by purpose, by value. They touch on philosophy and ethics and even aesthetics. Different people, different cultures, different philosophical traditions answer them differently. But here's what we can say with confidence: the universe is remarkable. It has produced stars from simple hydrogen. It has created elements through nuclear fusion. It has assembled those elements into planets and eventually into living organisms. It has generated complexity from simplicity, order from chaos, consciousness from unconscious matter. Whatever else we might say about it, whatever ultimate meaning or lack thereof we might attribute to it, the universe is astonishing in its capacity for self-organization and emergent complexity. The supermassive black hole at Andromeda's center is a part of this remarkable story. It formed from the collapse of matter in the early universe. It grew through accretion and mergers. It influenced the evolution of its host galaxy. It warped spacetime into exotic geometries we're still learning to understand. It represents one of the extreme states of matter, conditions so far from everyday experience that we need our most advanced theories just to begin describing them. And we, temporary arrangements of atoms on a small planet in an average galaxy, have figured out that it's there. We've measured its mass. We've observed its effects on surrounding stars. We've incorporated it into our models of cosmic evolution. This is an achievement worth pausing to appreciate, worth recognizing as something extraordinary. The tools we've used to accomplish this understanding are themselves remarkable. Telescopes that can detect photons from 2.5 million light-years away. Spectrographs that can analyze the composition and velocity of distant stars. Computers that can simulate billions of years of galaxy evolution. Mathematical frameworks that can describe the curvature of spacetime near black holes. All of these are human inventions, products of our curiosity and our drive to understand. But perhaps the most important tool is simply the willingness to ask questions, to look up at the night sky and wonder what's out there, to see patterns and seek explanations, to imagine journeys to places we can never physically visit. This capacity for curiosity, for wonder, for constructing mental models of things beyond our direct experience, this might be the most distinctly human trait, the thing that most sets us apart from other life on Earth. And Andromeda rewards that curiosity. Every observation reveals new details, new puzzles, new aspects of this vast galaxy that we didn't anticipate. Recent studies have found evidence of unusual stellar populations in the bulge, stars with strange chemical compositions that don't fit our models. Other observations have revealed more satellite galaxies than we expected, more stellar streams, more signs of past mergers and violent interactions. The more closely we look, the more complex the picture becomes. This is how science advances, not through definitive final answers but through increasingly detailed and accurate descriptions, through models that better match observations, through the gradual refinement of our understanding. We'll never have a complete perfect theory of how Andromeda formed and evolved because the system is too complex, the timescales too vast, the number of interacting components too large. But we can continue to improve our understanding, continue to chip away at the mysteries, continue to push back the boundaries of the unknown. The same is true for black holes. Our understanding has advanced tremendously since they were first predicted as mathematical curiosities in Einstein's equations. We've detected them through their effects on companion stars in binary systems. We've observed the supermassive ones at galaxy centers. We've even recently managed to image the event horizon itself, using a planet-scale array of radio telescopes to create a picture of the black hole at the center of the M87 galaxy. That image, showing a dark circle surrounded by a glowing ring of light, represents one of the triumphs of modern astronomy. Confirmation that these bizarre objects really do exist in the form Einstein's equations predicted. But questions remain. What happens to information that falls into a black hole? Does it disappear, violating principles of quantum mechanics, or is it somehow preserved, perhaps encoded on the event horizon surface? Do black holes eventually evaporate through Hawking radiation, slowly losing mass as quantum effects near the event horizon create particle-antiparticle pairs? If so, what happens when they've evaporated completely? What's left? These aren't just abstract theoretical questions. They touch on fundamental issues about the nature of reality, about whether information is truly conserved in the universe, about the relationship between quantum mechanics and gravity. Resolving them will require new physics, a theory that successfully combines quantum mechanics and general relativity into a coherent whole. Several candidates exist, string theory and loop quantum gravity among them, but none has yet achieved broad acceptance or made predictions that we can test experimentally. So we return to humility, to recognition that for all we've learned, much remains unknown. The center of Andromeda holds its secrets close, revealing them only gradually to our patient observations and careful reasoning. The supermassive black hole remains mysterious despite our models and equations. The history of the galaxy's formation and evolution is still being pieced together from fragmentary evidence. But this is not cause for despair. This is cause for excitement. We live in an age where many profound mysteries remain, where exploration, both physical and intellectual, continues to reveal surprises, where the universe still has secrets to share with those curious enough to seek them. Future observations will undoubtedly answer some of our current questions about Andromeda. More powerful telescopes will resolve individual stars in the galactic core, allowing us to study their motion and composition in greater detail. Better computer simulations will model the galaxy's evolution with increasing accuracy. New theoretical frameworks might explain the relationship between supermassive black holes and their host galaxies. Advanced gravitational wave detectors might even allow us to hear black holes merging in distant galaxies, adding a new sense to our exploration of the cosmos. And eventually, possibly within the next few centuries, if our species survives and continues to develop technology, we might send actual physical probes beyond our galaxy, tiny spacecraft pushed by lasers or carried by other exotic propulsion systems, traveling for millennia across the intergalactic void to reach Andromeda and send back close-up observations. It seems like science fiction now, but so did images of Pluto or landings on Mars just a few generations ago. The arc of technological development suggests that what seems impossible today might become routine tomorrow. Imagine what those probes might see. Imagine close-up views of Andromeda's spiral arms, detailed images of stellar nurseries where new stars are born, observations of the supermassive black hole from within the galaxy itself. Imagine the data they would send back, the discoveries they would make, the questions they would answer, and the new mysteries they would reveal. But even without such probes, even limiting ourselves to observations from Earth and Earth orbit, we can continue our exploration of Andromeda. Each new generation of instruments reveals details invisible to earlier ones. Each advance in theoretical understanding allows us to extract more information from existing observations. The journey continues, and we're privileged to be part of it, to live in an age when the universe's secrets are gradually being revealed through human ingenuity and determination. The collision between Andromeda and the Milky Way, that inevitable merger billions of years in the future, represents both an ending and a beginning. Two galaxies, each with its own history spanning billions of years, will merge to form something new. The process will be violent by astronomical standards, though slow enough that no human observer would notice dramatic changes over a lifetime. Gas clouds colliding, stars being flung into new orbits, both galaxies losing their spiral structure and reforming as an elliptical galaxy, a different type of galaxy with its own characteristics and properties. The supermassive black holes will eventually merge, as we discussed, creating gravitational waves that will carry the news of this cataclysmic event across the universe at the speed of light. By then, 4 billion years from now, those waves will have no humans to detect them, at least not humans as we currently exist. Evolution won't stop. If our descendants survive, they'll be as different from us as we are from the earliest primates. They might not even be biological anymore, might have transcended flesh and merged with machines or uploaded their consciousnesses into digital substrates. Or they might have gone extinct, another failed experiment in the universe's vast laboratory of possibilities. But the merger will happen regardless. The universe doesn't need observers. It proceeded for billions of years before life arose, before consciousness emerged, before anyone was around to witness its wonders. And it will continue for trillions of years after all the stars have died and the black holes have evaporated and nothing remains but thin clouds of elementary particles in an expanding, cooling, darkening cosmos. This is the ultimate fate predicted by our best current cosmological models: heat death, the gradual dissipation of all structure and order as entropy inevitably increases. The stars will die. The galaxies will disperse. The black holes will evaporate. The universe will grow cold and dark and empty. Not tomorrow, not for trillions upon trillions of years, but eventually, inevitably, if our physics is correct. Should this fill us with despair? Should the cosmic perspective, the recognition of our insignificance in space and time, diminish our lives and make our concerns seem trivial? Some have argued yes, that awareness of cosmic insignificance leads necessarily to nihilism, to the conclusion that nothing matters if the universe will eventually end in cold darkness. But this seems like a failure of imagination, a confusion between cosmic significance and human significance. The universe doesn't need to be eternal for our lives to have meaning. The eventual heat death of the cosmos doesn't make love less real, art less beautiful, discovery less exciting, kindness less valuable. Meaning is something we create, not something we discover in the arrangement of galaxies or the laws of physics. We give meaning to our lives through our choices, our relationships, our creations, our attempts to understand and improve the world around us. The fact that the universe is vast and old and will outlast us by unimaginable timescales doesn't diminish this. If anything, it makes it more precious, more remarkable that we exist at all, that the universe has produced beings capable of contemplating its nature and wondering about their place in it. The journey to the center of Andromeda has been a journey of imagination, but it's grounded in real observations, real physics, real data collected by real astronomers working patiently over decades and centuries. The supermassive black hole we've been discussing isn't a fantasy. It's there, right now as you read this, 2.5 million light-years away, warping spacetime, pulling on the stars around it with irresistible gravitational force, holding secrets about the nature of reality in the ultimate extremes of density and curvature. We've used that black hole, and Andromeda more broadly, as a lens through which to explore themes that go beyond astronomy, the nature of knowledge, the limits of understanding, the relationship between observer and observed, the meaning of existence in a vast and ancient universe. These themes arise naturally when contemplating the cosmos because the cosmos is so far beyond human scale that it forces us to think differently, to expand our perspectives, to question assumptions we didn't even know we were making. What is a galaxy, really? Is it just a collection of stars and gas and dark matter, or is it something more, a coherent entity with its own life cycle? Birth and evolution and eventual death. Galaxies merge, forming larger systems. They consume smaller galaxies. They evolve over time as stars form and die. In some sense, they're more dynamic, more alive than we typically acknowledge. Not alive in the biological sense, obviously, but possessing a kind of existence that transcends the components that make them up. This is emergence, the phenomenon where complex systems exhibit properties and behaviors that their individual components don't possess. A single neuron isn't conscious, but billions of them working together create consciousness. A single star doesn't have a spiral arm, but trillions of them can create a spiral galaxy. The whole is more than the sum of its parts, exhibiting new properties that arise from the interactions between components. Andromeda is an emergent structure, a pattern that arises from gravity acting on matter over cosmic timescales. The supermassive black hole at its center might have formed through a series of smaller mergers, each black hole contributing to the final mass, the whole growing larger than any individual component. The spiral arms emerge from density waves, patterns that exist independently of the stars that trace them out. The galaxy is a process as much as an object, constantly changing, constantly evolving, never static even though it appears frozen in our brief observations. Understanding this dynamic nature, this constant evolution, helps us appreciate what we're seeing when we observe Andromeda. We're not looking at a finished product but at a snapshot of an ongoing process, a moment frozen in time by the finite speed of light. Andromeda as we see it now represents the galaxy as it existed 2.5 million years ago. The light that reaches our telescopes tonight left Andromeda when our ancestors were primitive hominids, probably Australopithecus or early Homo, just beginning to use stone tools, just starting down the path that would eventually lead to us. What does Andromeda look like now, in our current moment? We can't know. The light showing us its current state won't reach Earth for another 2.5 million years. We're always looking at the past when we look at astronomical objects, always seeing them not as they are but as they were. For nearby objects like the Sun, the delay is negligible, just 8 minutes. For distant galaxies, the delay becomes significant, millions or billions of years. The most distant objects we can observe show us the universe as it existed when it was young, less than 1 billion years after the Big Bang. Those galaxies might not even exist anymore in their original form, might have merged or evolved beyond recognition in the billions of years since the light we're now receiving was emitted. This is the peculiar nature of astronomical observation. We're archaeologists as much as scientists, examining ancient light for clues about the past. We can't interact with the objects we study, can't perform experiments on them, can only collect the photons that happen to reach us and extract whatever information they contain. It's detective work on a cosmic scale, piecing together the history and nature of the universe from fragmentary evidence. And yet, remarkably, it works. We've constructed a detailed and accurate picture of cosmic evolution from the Big Bang to the present, from the first atoms forming in the cooling early universe to the structure we see today. We understand, at least in broad outline, how galaxies formed, how stars create heavy elements, how planets coalesce from debris disks around young stars. We know the universe is expanding and can measure that expansion. We know its age to within a few million years out of 13.8 billion. We know its composition, how much is normal matter, how much is dark matter, how much is dark energy. This is an astonishing achievement, worthy of celebration and recognition. Future generations, if they exist, will look back at this era as the time when humanity first comprehended the cosmos on large scales, when we figured out the basic story of the universe's evolution, when we discovered that the same physical laws that govern falling apples and orbiting moons also govern the formation of galaxies and the merger of black holes. But they'll also see our limitations, our gaps in knowledge, the mysteries we couldn't solve. Just as we look back at early astronomers and smile at their Earth-centered models in crystalline spheres, future scientists will smile at our confusion about dark matter and dark energy, at our inability to reconcile quantum mechanics and general relativity, at our crude understanding of how the first stars formed and how supermassive black holes grew to their enormous masses so quickly in the early universe. This is the nature of science, always provisional, always incomplete, always subject to revision when new evidence emerges. We don't have final answers, don't claim to have perfect knowledge. We have models that work, theories that match observations, frameworks that allow us to make predictions and explain phenomena. When those models fail, when observations don't match predictions, we revise the models. We're always working with approximations, with simplifications of reality that capture the essential features while ignoring complications we can't yet handle. The journey to Andromeda's center has illustrated this beautifully. We started with simple observations of a fuzzy patch in the night sky. We progressed to understanding it as a separate galaxy. We discovered the spiral structure, the central bulge, the halo of old stars and globular clusters. We inferred the presence of dark matter from rotational velocities. We deduced the existence of a supermassive black hole from stellar orbits in the core. Each step built on previous ones, each discovery enabling the next, each answer revealing new questions. And the journey continues. New observations with better telescopes resolve more details, reveal more structure, uncover more complexity. Better theories explain previously mysterious phenomena, connect disparate observations into coherent pictures, make predictions that can be tested. The cycle of observation and theory, data and interpretation, question and answer, continues indefinitely. There is no final destination, no point where we'll know everything and can stop exploring. The universe is too rich, too complex, too vast for any finite understanding to encompass completely. Perhaps this is as it should be. Perhaps a universe small enough to completely understand would be boring, unsatisfying, insufficient to hold our interest. Perhaps the presence of mystery, of things we don't yet know and might never know, is what makes science exciting, what drives us to keep exploring, keep questioning, keep searching for deeper understanding. The supermassive black hole at Andromeda's center stands as a symbol of this mystery. It's there, we know it's there, we can measure its effects and calculate its properties. Yet we cannot see it directly, cannot probe its interior, cannot answer fundamental questions about what happens at the singularity where all its mass is concentrated. It represents the limits of our knowledge, a boundary we can approach but not cross, a place where our theories break down and new physics is needed. But limits exist to be pushed against, boundaries to be tested, frontiers to be explored. What seems impossible today might become routine tomorrow. What questions seem unanswerable now might have clear answers in a century or a millennium. We cannot predict what future discoveries will reveal because by definition they'll tell us things we don't currently know. We can only maintain our curiosity, our willingness to be surprised, our openness to having our assumptions overturned. Andromeda will merge with the Milky Way. This is certain. The gravitational dance of the two galaxies, played out over billions of years, will inevitably bring them together. Stars will be scattered into new orbits. Gas will collide and form new stars. The supermassive black holes will spiral together and merge. And from the chaos, a new galaxy will emerge, different from either of its parents, a hybrid structure that combines the mass and complexity of both. This is how galaxies grow, through mergers and collisions, through the gradual accumulation of matter and the violent mixing of stellar populations. It's happening throughout the universe. All the time. Galaxies are colliding right now, though we only see the light from millions or billions of years ago. The universe is a violent place on large scales, full of collisions and explosions and catastrophes that dwarf anything we experience on Earth. Yet from this violence comes structure, comes complexity, comes the conditions necessary for stars and planets and eventually life. Is this process purposeful? Does the universe have some goal, some end state it's evolving toward? Most scientists would say no, that purpose is something we project onto the cosmos rather than something inherent in it. The universe simply is, following physical laws, evolving according to the behavior of matter and energy under various conditions. It doesn't have intentions or goals any more than a river has intentions or a hurricane has goals. Things happen because the laws of physics say they must, not because of some cosmic purpose or design. But others argue that the emergence of complexity, the spontaneous organization of matter into stars and galaxies and living organisms, suggests something more than random chance. The laws of physics could have been different, could have had different constants or different forms. Yet they're precisely calibrated to allow for the complexity we observe. Change certain fundamental constants by small amounts, and stars couldn't form, or carbon couldn't be created, or molecules couldn't be stable. The universe seems fine-tuned for complexity, for life, for consciousness. Does this fine-tuning imply design? Does it require a designer? Or is it simply selection bias, the fact that we necessarily find ourselves in a universe capable of producing observers because otherwise we wouldn't be here to ask the question? These are deep questions, philosophical rather than scientific, questions that might not have definitive answers. What we can say is that the universe is remarkable. Andromeda is remarkable. The journey from the Big Bang to the present, from a hot dense state to the rich complexity we observe today, is remarkable. The fact that matter can organize itself into structures like galaxies and stars, that it can eventually produce living things, that those living things can develop intelligence and consciousness and curiosity, that we can sit here and contemplate the center of a galaxy 2.5 million light-years away, all of this is extraordinary. Perhaps that's enough. Perhaps we don't need ultimate answers about purpose and meaning. Perhaps the journey itself, the exploration, the discovery, the gradual expansion of knowledge and understanding, perhaps that's sufficient. Perhaps the meaning is in the asking rather than in any final answer. The center of Andromeda waits in the darkness between stars, patient and eternal on human timescales. The supermassive black hole continues its gravitational reign, holding together the galaxy through invisible forces. Stars orbit, are born, live, die, in cycles that span billions of years. And somewhere, on a small planet orbiting a yellow star in a neighboring galaxy, beings evolved from ancient life forms look up at the night sky and wonder, asking questions, seeking understanding, continuing a journey that began when the first conscious minds emerged and looked at the stars with curiosity. We are part of that journey, contributors to humanity's collective project of understanding the cosmos. Each generation adds its discoveries to the accumulated knowledge, each scientist contributes observations and theories, each question answered opens new questions to explore. We stand on the shoulders of those who came before, and future generations will stand on ours. The journey to the center of Andromeda, then, is not just about one galaxy or one black hole. It's about the human drive to understand, to explore, to push beyond the boundaries of the known. It's about curiosity and wonder and the refusal to accept ignorance when knowledge is possible. It's about our place in the cosmos and our relationship with the universe that created us. And in the end, perhaps that's the most profound realization of all, we are not separate from the universe but part of it. Manifestations of its complexity, examples of what matter can accomplish when organized in particular ways. When we study Andromeda, we're studying ourselves, learning about the processes that shaped not just that distant galaxy but our own, understanding the forces that govern all galaxies including the one we call home. The supermassive black hole at Andromeda's center is our distant cousin, formed through similar processes to the one at the Milky Way's core, subject to the same physical laws, shaped by the same cosmic evolution. The stars surrounding it are siblings to our Sun, born from similar clouds of hydrogen and helium, following similar life cycles. The atoms that make up Andromeda are the same types of atoms that make up us, created in stellar furnaces, scattered by supernovae, recycled through multiple generations of stars. We are connected to Andromeda in ways both literal and metaphorical. We are connected to the entire universe, part of its fabric, participants in its ongoing evolution. Our consciousness is the universe becoming aware of itself. Our understanding is the universe understanding itself. Our wonder at the cosmos is the cosmos wondering at itself through us. This is not mysticism or poetry, though it may sound like both. It's simply recognition of the facts, We are made of matter from the universe, organized by processes that occur throughout the universe, following laws that govern the entire universe. When we think about Andromeda, atoms in our brains, atoms created in ancient stars, rearrange themselves in patterns that correspond to our understanding of that distant galaxy. Physical matter is representing distant physical matter through the medium of consciousness and thought. How this works, how matter can become conscious and think about itself, remains one of the deepest mysteries in science. We don't know how subjective experience arises from objective physical processes. We don't know why we're conscious rather than simply behaving like philosophical zombies, performing the same actions but without any inner experience. We don't even fully understand what consciousness is, how to define it, whether it's unique to humans or shared by other animals or potentially even present in some form throughout the universe. These questions about consciousness connect back to our questions about the universe itself, about meaning and purpose and whether there's something more than just particles and forces. If consciousness can arise from purely physical processes, if subjective experience can emerge from objective matter, then perhaps the universe is stranger, more wonderful, more mysterious than our current physics suggests. Perhaps there are aspects of reality we haven't yet discovered, levels of organization and complexity we haven't yet imagined. Or perhaps consciousness is simply what information processing feels like from the inside, an emergent property of sufficiently complex systems organizing and representing information about themselves and their environment. Perhaps there's no deep mystery, just the recognition that we don't yet fully understand how brains work, how neurons cooperating produce thoughts and feelings and experiences. Perhaps future neuroscience will explain consciousness completely in physical terms, demystify it, reduce it to algorithms and neural networks and electrochemical signals. But even if consciousness can be fully explained physically, even if we someday understand exactly how brains produce minds, the phenomenon itself remains remarkable. The fact that the universe can produce beings capable of understanding the universe, that matter can organize itself into forms that contemplate matter, that we exist at all and can ask these questions, this is extraordinary regardless of the ultimate explanation. And it brings us full circle, back to Andromeda, back to that galaxy spinning in the darkness, back to the journey we've been taking through imagination and science to its heart. Because understanding Andromeda, understanding galaxies and black holes and the large-scale structure of the cosmos, is part of understanding ourselves. We cannot fully know what we are without knowing where we came from. And we cannot know where we came from without understanding cosmic evolution, galaxy formation, star birth, the creation of heavy elements in stellar cores. We are stardust. This is literal truth, not metaphor. The atoms in our bodies were forged in stars that died before the sun existed, scattered across space by supernovae, eventually incorporated into the molecular cloud that collapsed to form our solar system. We are part of the cosmic cycle, temporary patterns in the flow of matter and energy that has been ongoing for billions of years and will continue for billions more. The journey to the center of Andromeda has been a journey of understanding this cycle, this cosmic story of which we're a part. It's been a journey through space and time, from the edge of a galaxy to its core, from the present moment back through billions of years of history. It's been a journey through physics, from the familiar gravity of everyday experience to the extreme warping of spacetime near a black hole. It's been a journey through scales, from the human scale we inhabit to the vast galactic scale where distances are measured in thousands of light-years. But most importantly, it's been a journey of perspective, an attempt to see ourselves and our place in the universe more clearly. By contemplating something so vast, so distant, so far beyond human scale, we gain perspective on our own existence, on what matters and what doesn't, on the grand sweep of cosmic evolution and our tiny but significant role in it. So as our imaginary journey comes to an end, as we pull back from the supermassive black hole at Andromeda's center, retreat through the dense stellar populations of the bulge, traverse the spiral arms one more time, and return to our own galaxy, our own solar system, our own small blue planet, we carry this perspective with us. We've seen the heart of another galaxy. We've contemplated mysteries that challenge our deepest understanding of physics. We've touched, if only intellectually, the most extreme phenomena in the universe. And we recognize that all of it, the entire cosmos with its galaxies and stars and black holes, its dark matter and dark energy, its expansion and evolution, all of it is comprehensible, at least in principle, to beings like us. The universe follows rules we can discover. It operates according to laws we can understand. It's vast and ancient and strange, but it's not arbitrary, not chaotic, not beyond our capacity to investigate and explain. This is the gift of science, the legacy of centuries of careful observation and bold theorizing, the recognition that we can understand the cosmos, that we're not condemned to ignorance, that the universe is knowable. Not completely, not perfectly, not finally, but progressively, asymptotically, approaching better and better approximations of truth through patient investigation and careful reasoning. The supermassive black hole at Andromeda's center will continue its patient wait, pulling on stars with irresistible gravity, slowly consuming any matter that ventures too close, maintaining its enigmatic presence at the galaxy's heart. It doesn't know we're studying it, doesn't care about our theories and observations, simply exists according to the laws of physics, following its predetermined path through spacetime. But we know it's there. And that knowledge, that understanding, that successful reaching across 2.5 million light-years to comprehend something so distant and strange, that represents one of humanity's greatest achievements. We looked up at a fuzzy patch in the autumn sky and discovered a galaxy. We analyzed the motion of stars and discovered a black hole. We applied physics and mathematics and found connections, found patterns, found understanding. And the journey continues, as it must, as it always will, as long as there are curious minds asking questions and seeking answers. New discoveries await. New mysteries will emerge. The universe will continue to surprise us, to challenge our understanding, to reveal aspects of reality we never imagined. And we will continue to explore, to observe, to theorize, to gradually expand the sphere of human knowledge into the vast unknown that surrounds us. This is our nature. This is our purpose, if we need one. Not assigned from outside, not granted by the universe, but chosen by us, inherent in our consciousness, built into our brains by evolution and refined by culture, the drive to understand, to explore, to know. And somewhere out there, in the heart of Andromeda, at the center of 2 trillion stars, a black hole waits, patient and eternal, holding secrets we've barely begun to uncover, representing mysteries we'll spend centuries more investigating, standing as a testament to both the universe's strangeness and our ability to comprehend it. The journey is never over. There is always farther to go, deeper to probe, more to discover. And that, perhaps more than any specific fact about black holes or galaxies, is the real lesson of our voyage to Andromeda's center, that the universe is infinite in its capacity to surprise, that knowledge is endless in its frontiers, that wonder never needs to fade as long as we maintain our curiosity and our courage to ask difficult questions. So look up at Andromeda tonight, if your skies are dark and clear enough to see that faint smudge of light. Remember that you're seeing 2 trillion stars, seeing a galaxy that will someday merge with our own, seeing light that traveled for 2.5 million years to reach your eyes. Remember the supermassive black hole at its center, the mystery and the mathematics, the observational evidence and the theoretical framework. Remember the dark matter that holds it together and the cosmic evolution that shaped it. But most of all, remember that you can understand this, that a being evolved on Earth to survive in forests and savannas can nonetheless comprehend the center of a distant galaxy. Remember what that says about the universe, that it's governed by laws we can discover. Remember what that says about us, that we have the capacity to discover those laws and apply them across cosmic distances. We are children of the universe, products of its evolution, examples of its complexity. We are also its students, learning its secrets, uncovering its patterns, gradually piecing together the grand story of cosmic history. And in our understanding, in our knowledge, in our ability to journey intellectually to places we can never physically visit, we fulfill a potential that has been building for 13.8 billion years, since the moment of the Big Bang itself. The center of Andromeda waits for us, not in space but in understanding, not as a physical destination but as an intellectual one. And we have reached it, if only partially, if only incompletely. We have made the journey. We have gazed into the heart of another galaxy and glimpsed its secrets. And that journey, that achievement, stands as proof of what consciousness can accomplish, what understanding can achieve, what the human mind can grasp when it dares to reach beyond the familiar into the vast unknown that surrounds us on all sides. This is our legacy. This is our achievement. This is the journey to the center of Andromeda, and it is glorious. Yet something remains unspoken, something hovering at the edges of our understanding like a half-remembered dream. We've journeyed to Andromeda's core, confronted its supermassive black hole, traced the spiral arms and contemplated the dark matter halo. But what about the space between? What about the vast intergalactic void we traverse to reach this destination, that emptiness that separates galaxy from galaxy, that seems like nothing but contains everything we need to understand the universe's ultimate fate? The void is not empty. This is the first revelation, the first crack in our intuitive understanding of space. Between Andromeda and the Milky Way, across those 2.5 million light-years of apparent nothingness, matter exists. Thin beyond imagining, more tenuous than any vacuum we can create on Earth, but present nonetheless. Hydrogen atoms drift through the intergalactic medium, perhaps one per cubic meter, perhaps fewer. This seems like nothing, like a void so complete that calling it empty would be justified. But multiply that single atom by the volume of space between galaxies. And suddenly we're talking about mass, about matter, about substance. This intergalactic medium isn't primordial, isn't leftover hydrogen from the Big Bang floating unchanged since the universe's first moments. It's been processed, enriched, polluted if you will, by billions of years of galactic activity. Supernovae in Andromeda and the Milky Way have ejected material into intergalactic space. Galactic winds, driven by the combined effects of supernova explosions and stellar radiation, push gas outward beyond the galaxy's gravitational grasp. Active galactic nuclei, those periods when supermassive black holes feed voraciously, generate jets and outflows that extend millions of light-years into surrounding space. So the atoms floating in the intergalactic void carry stories, chemical signatures of their creation in stellar cores, evidence of their violent ejection from galaxies, markers of cosmic recycling that operates on the largest scales. An oxygen atom drifting in intergalactic space might have formed in a massive star in Andromeda 5 billion years ago, been scattered by that star's supernova death, pushed outward by subsequent stellar winds, and now hangs suspended in the darkness, waiting. Waiting for what? Perhaps to be captured by the gravitational pull of a galaxy group, to fall back into a galactic disk, to be incorporated into a molecular cloud, to become part of a new star or planet or eventually a living organism. The cosmos recycles everything. Nothing is wasted. Nothing is truly lost. Matter changes form, shifts location, transforms from one state to another, but persists. The atoms that compose your body have existed since shortly after the Big Bang, have been part of countless structures and systems before you, will continue existing long after you dissolve back into the cosmic mix. You are a temporary arrangement, a pattern that persists for decades before dissipating, but the substrate remains, the underlying matter continues, immortal in a way that individuals never are. Does this perspective comfort or disturb? Does the recognition that we're temporary patterns in eternal matter diminish our significance or enhance our appreciation of the brief time we have? The question admits no universal answer, depends on temperament and philosophy and what one seeks from existence. But return now to that intergalactic medium, to those sparse atoms floating between galaxies. They're not alone. Radiation pervades the void as well, photons traveling in all directions, carrying energy from the Big Bang itself and from every luminous object in the universe. The cosmic microwave background, that echo of the universe's fiery birth, fills all of space with photons that have been traveling and cooling for 13.8 billion years. What started as intense gamma radiation in the hot early universe has redshifted, stretched by cosmic expansion, until now it appears as microwave radiation with a temperature just under 3 degrees above absolute zero. These photons are everywhere, streaming through your body right now at the speed of light, countless billions of them every second, imperceptible without specialized instruments but undeniably present. They carry information about the early universe, tiny variations in temperature that correspond to density fluctuations in the primordial plasma, seeds that would eventually grow into galaxies and galaxy clusters. By mapping these temperature variations across the entire sky, astronomers have reconstructed the universe as it appeared just 380,000 years after the Big Bang, long before the first stars formed, long before galaxies existed, when everything was still hot plasma gradually cooling and becoming transparent to light. This is remarkable when you pause to consider it. We can see further back in time than seems possible, can observe the universe in its infancy, can measure properties of the early cosmos with stunning precision. The cosmic microwave background tells us the universe's age, its composition, its geometry, its rate of expansion. It confirms predictions of Big Bang cosmology with such accuracy that the model has become essentially unassailable in its broad outlines, even as details remain debated and refined. And those photons travel through the intergalactic void, through the space between Andromeda and the Milky Way, unimpeded by the sparse matter, carrying their ancient message to any observer capable of detecting them. They've witnessed the entire history of cosmic evolution, been present since the moment the universe became transparent, traversed expanding space while galaxies formed and evolved and collided around them. But there's more in the void than just sparse matter and ancient photons. There are also magnetic fields, impossibly weak by terrestrial standards but present nonetheless, threading through intergalactic space, organizing charged particles, creating structure on the largest scales. Where do these magnetic fields come from? How did they originate? We don't fully know. Perhaps they were seeded in the early universe through quantum fluctuations. Perhaps they grew through dynamo effects in the first galaxies and then spread into intergalactic space. Perhaps some combination of processes created and amplified them over cosmic history. These fields are invisible, detectable only through their effects on charged particles and on the polarization of radio waves passing through them. Yet they might play crucial roles in cosmic evolution, in how galaxy clusters form and evolve, in how energy and matter distribute themselves across the universe. We're only beginning to map intergalactic magnetic fields, only starting to understand their properties and origins. It's another frontier, another mystery at the largest scales. The journey from the Milky Way to Andromeda, then, isn't a journey through emptiness but through a complex medium filled with matter and radiation and fields, a medium that connects galaxies rather than separating them, that facilitates exchange and interaction and eventual merger. The two galaxies aren't isolated islands but parts of a larger structure, the local group, a collection of more than 50 galaxies bound together by mutual gravity. Most of these galaxies are dwarfs, small systems containing millions rather than billions of stars, satellites orbiting the two giants Andromeda and the Milky Way. These dwarf galaxies have their own stories, their own histories of formation and evolution. Many have been tidally disrupted by their massive neighbors, stretched and torn by differential gravitational forces, their stars scattered into streams that wrap around the larger galaxies. We've seen evidence of this in our discussion of Andromeda's stellar streams, those ghostly arcs marking the remnants of consumed satellites. But the dwarf galaxies that remain intact offer important clues about galaxy formation in the early universe. Because they're small, they're less efficient at forming stars, retain more of their primordial composition, show us what galaxies might have looked like billions of years ago when the universe was younger. They're cosmic fossils, relics of an earlier era, surviving in the shadows of their massive neighbors. And they're dark matter dominated. In fact, the smallest dwarf galaxies are the most dark matter dominated systems known, containing hundreds of times more dark matter than normal matter. This makes them ideal laboratories for studying dark matter's properties, for testing theories about what it might be, for searching for signals of dark matter particles annihilating or decaying. If dark matter consists of weakly interacting massive particles, as many theories suggest, those particles should occasionally collide and annihilate, producing gamma rays or other signals we might detect. Dwarf galaxies, with their high dark matter densities and low backgrounds of normal matter, offer the best prospects for seeing such signals. Yet despite decades of searching, we haven't detected dark matter particles directly. Not in laboratory detectors deep underground. Not in space-based telescopes looking for annihilation signals. Not in particle accelerators like the Large Hadron Collider. Dark matter remains stubbornly invisible except through its gravitational effects. This is frustrating and fascinating in equal measure. We know dark matter exists. Can measure how much of it there is, can map its distribution through gravitational lensing studies. But we don't know what it is, what particles compose it, why it interacts so weakly with normal matter. Perhaps it's not particles at all, at least not in the conventional sense. Perhaps it's something more exotic, primordial black holes created in the early universe, or modifications to gravity that become important on galactic scales, or something we haven't imagined yet because we lack the conceptual framework to even think about it. Science progresses through successive approximations, through models that work until they don't, through frameworks that explain observations until new observations demand new frameworks. Dark matter is telling us something fundamental about the universe, something our current theories don't fully capture. What that something is remains one of the great open questions in physics, a mystery that has persisted for nearly a century since Fritz Zwicky first inferred the existence of unseen matter from the motions of galaxies in the Coma cluster. We've made progress, certainly, mapped dark matter's distribution, understood its role in structure formation, recognized its importance to cosmic evolution. But the fundamental nature of dark matter remains unknown, hidden behind a wall of technical challenges and theoretical uncertainties. Consider what this means: the dominant form of matter in the universe, the substance that outweighs everything we can see by a factor of 6 to 1, is completely unknown to us. We live in a universe where most of the matter is invisible and unidentified, where the stars and planets and gas clouds and everything we can observe directly represent just a small fraction of what exists. It's humbling and exciting simultaneously, a reminder of how much we still have to learn, how many fundamental discoveries remain to be made. And dark matter is just one mystery. Dark energy, that mysterious force driving the universe's accelerating expansion, is even more enigmatic. Discovered only in 1998 through observations of distant supernovae, dark energy represents roughly 70% of the universe's total energy content. Yet we have no idea what it is. We can measure its effects, can quantify how much the universe's expansion is accelerating, can incorporate it into our cosmological models. But we don't understand its nature, don't know if it's a property of space itself or a new field permeating the universe or something completely different. Think about what we're saying: we understand about 5% of the universe's content, the normal matter that makes up stars and planets and us. 25% is dark matter, which we know exists but can't identify. 70% is dark energy, which we've barely begun to study. The universe is 95% mystery, 95% unknown territory, 95% frontier waiting to be explored. This should be encouraging rather than discouraging. We're not running out of things to discover, not approaching the end of physics where all the fundamental questions have been answered. We're living in an era of profound ignorance about the universe's basic composition, which means we're living in an era ripe for revolutionary discoveries, for breakthroughs that will transform our understanding as dramatically as relativity and quantum mechanics did a century ago. What will those breakthroughs look like? We can't know, almost by definition. If we could predict revolutionary discoveries, they wouldn't be revolutionary. They'll come from unexpected directions, from observations that don't fit existing theories, from experiments that produce surprising results, from theoretical insights that connect previously disparate phenomena. They'll require patience and persistence and probably luck, as most major discoveries do. But they'll come, eventually, because the universe is there waiting to be understood, and humans are curious enough and clever enough to eventually figure it out. The journey to Andromeda's center has taken us through this mysterious universe, past dark matter halos and through intergalactic medium enriched by billions of years of galactic evolution, toward a supermassive black hole that represents the extreme end of gravitational collapse. But it's also taken us through the landscape of human understanding, from what we know with confidence to what we suspect to what we admit we don't know at all. Science isn't about having all the answers. It's about asking good questions, about developing methods to investigate those questions, about building frameworks that organize knowledge and reveal patterns and make predictions. It's about being honest about uncertainty, about distinguishing between what we know and what we think we know and what we're just guessing at. It's about revision and correction, about changing our minds when evidence demands it, about following the data even when it leads to conclusions we find uncomfortable or surprising. The history of astronomy illustrates this beautifully. We once thought Earth was the center of everything. We were wrong. We once thought the Milky Way was the entire universe. We were wrong. We once thought the universe was static and eternal. We were wrong. We once thought normal matter was all that existed. We were wrong. Each time, observations forced us to revise our understanding, to expand our perspective, to recognize that reality is stranger and more wonderful than we had imagined. What are we wrong about now? What current assumptions will future generations look back on and shake their heads at? We can't know specifically, but we can be certain that some of our current understanding is incomplete or incorrect or misguided. This isn't a failure of science. It's a feature, not a bug. Science advances by being wrong in interesting ways, by making predictions that can be tested, by building on previous knowledge while remaining open to radical revision when necessary. Perhaps our understanding of black holes will turn out to be incomplete. Perhaps the singularity at the center, where our theories predict infinite density and infinite curvature, doesn't actually exist. Perhaps quantum effects become important before that point, creating some kind of quantum core with strange properties we can't currently calculate. Perhaps information falling into black holes isn't lost but transformed and eventually released through Hawking radiation or some other mechanism we haven't discovered. Perhaps black holes are doorways to other universes or other regions of spacetime, creating connections that general relativity hints at but doesn't fully describe. These are speculations, ideas floating around in the physics community, hypotheses that might or might not turn out to be correct. What's certain is that our current understanding is incomplete, that mysteries remain, that the final word on black holes hasn't been written. The supermassive black hole at Andromeda's center holds secrets we haven't yet uncovered, represents phenomena we haven't fully explained, challenges us to develop better theories and make more precise observations. And then there's the question of what's inside. We've talked about the event horizon, that point of no return beyond which nothing can escape. We've mentioned the singularity, where all the black hole's mass is supposedly compressed into a point of infinite density. But what's the experience like for matter falling past the event horizon? What happens to information, to structure, to the organization of particles as they approach the singularity? From outside, we can never know. Information can't escape from within the event horizon, at least not in any classical sense. The interior of a black hole is causally disconnected from the external universe, a separate region of spacetime that can influence but not be influenced by anything outside. Throw a book into a black hole, and all the information it contained is lost to the outside universe, seemingly destroyed in violation of quantum mechanical principles that say information must be conserved. This is the black hole information paradox, one of the most vexing problems in theoretical physics. It pits general relativity against quantum mechanics, two of our most successful theories, each tested to incredible precision in their respective domains, yet fundamentally incompatible when it comes to black holes. General relativity says information can be destroyed. Quantum mechanics says it can't. Something has to give. Stephen Hawking wrestled with this paradox for decades, eventually proposing that information might be preserved in subtle correlations in the Hawking radiation that black holes emit. Others have suggested holographic principles, where all the information about the black hole's interior is somehow encoded on its two-dimensional event horizon surface. Still others propose that black holes don't have true singularities, that quantum gravity effects create some kind of exotic core that preserves information. The debate continues, unresolved, a testament to how much we still need to learn about the intersection of gravity and quantum mechanics. But perhaps we're asking the wrong questions. Perhaps the very concept of inside the black hole doesn't make sense in the way we imagine. Spacetime is warped so extremely near a black hole that our usual intuitions about space and time break down completely. The future time direction points toward the singularity. The radial space direction becomes timelike. Trying to visualize this using our everyday experience of 3 spatial dimensions and 1 time dimension leads to confusion and contradiction. We need new mathematics, new frameworks, new ways of thinking about spacetime in extreme conditions. String theory offers one possibility, suggesting that at very small scales, spacetime isn't smooth and continuous but made of tiny vibrating strings or higher dimensional objects. Loop quantum gravity offers another approach, quantizing spacetime itself into discrete chunks. Neither theory is complete or fully tested, but both represent attempts to go beyond our current understanding, to develop the next generation of physics that can handle black holes and the Big Bang and other extreme phenomena where both gravity and quantum effects are important. The supermassive black hole at Andromeda's center waits patiently for us to figure this out, doesn't care about our theoretical struggles, simply exists according to whatever the true laws of physics turn out to be. It's a natural experiment, a test case, a phenomenon we can observe and measure and use to constrain our theories. We can't do experiments on black holes in the laboratory, can't create them or manipulate them or study them up close. But nature has provided them, scattered throughout the universe, available for observation by anyone with sensitive enough instruments. And we've learned so much already from those observations. We've confirmed that black holes exist, not just as mathematical solutions to Einstein's equations but as real physical objects. We've measured their masses and spins. We've watched stars orbit around them. We've even imaged event horizons directly using very long baseline interferometry that combines radio telescopes across the Earth into a planet-sized instrument. The famous image of M87's black hole, that dark circle surrounded by a glowing ring, represents one of the great triumphs of observational astronomy, confirmation that black holes look the way our theories predict. But each answer raises new questions. That image showed asymmetry in the ring around M87's black hole, with one side brighter than the other. This matches predictions from general relativity about Doppler effects from the rotating accretion disk, but the details open new avenues of investigation. Can we use these observations to test alternatives to general relativity? Can we detect signatures of the black hole's spin? Can we observe temporal variations as matter falls in? Can we eventually image the black hole at Andromeda's center or at the Milky Way's core, comparing different systems and building up a catalog of black hole properties? These are the questions driving current research, the investigations occupying astronomers and astrophysicists worldwide. Every observation adds data, constrains theories, pushes our understanding forward incrementally. Revolutionary breakthroughs are rare, but steady progress is constant. We're building a comprehensive picture of black holes, galaxy by galaxy, observation by observation, theory by theory. And Andromeda remains central to this effort, not because it's unusual or exotic but precisely because it's typical. It represents a standard massive spiral galaxy with a standard supermassive black hole at its center. By understanding Andromeda, we understand galaxies in general. By studying its central black hole, we learn about supermassive black holes throughout the universe. It's close enough for detailed observations but far enough to give us perspective, to remind us that what we see in the Milky Way isn't unique, that the same processes operate everywhere, that the universe is fundamentally uniform on large scales. This uniformity, this consistency of physical laws across space and time, is one of the most remarkable features of the cosmos. Galaxies billions of light-years away, so distant we see them as they appeared when the universe was young, follow the same laws as nearby galaxies. Stars in Andromeda form the same way as stars in the Milky Way. The supermassive black hole at Andromeda's center obeys the same equations of general relativity as black holes everywhere else. This isn't something we could have predicted a priori. The universe could have been different in different places, could have had different laws in different epochs, could have been fundamentally heterogeneous and incomprehensible. But it isn't. And this uniformity enables science, makes it possible to extrapolate from local observations to cosmic conclusions, allows us to develop universal theories that apply everywhere. We test theories in our solar system and apply them to distant galaxies. We observe processes in nearby stars and assume similar processes occur in stars throughout the universe. This methodology works because the universe cooperates, because it is indeed uniform, because physical laws don't change from place to place or time to time. Why this is so remains a mystery. Why does the universe have laws at all? Why are those laws mathematical? Why are they comprehensible to creatures like us? These are questions science can't currently answer, questions that touch on philosophy and perhaps metaphysics. We can describe how the universe works without understanding why it works that way, can formulate equations without knowing where those equations come from, can discover patterns without comprehending why patterns exist at all. Perhaps someday we'll have deeper answers. Perhaps a theory of everything, if such a thing is possible, would explain not just what the laws of physics are but why they must be that way, why no other laws are possible or consistent. Perhaps we'll discover that our universe is one of many in a multiverse, each with different physical laws, and we inhabit this one simply because its laws allow for the existence of observers. Perhaps the questions are meaningless, based on faulty assumptions about causation and explanation. But these are speculations for future generations to explore. For now, we work with the universe we have, investigate its properties, discover its patterns, build theories that describe and predict its behavior. And Andromeda remains a key laboratory for this investigation, a cosmic experiment running on timescales of billions of years, accessible to our observations, revealing its secrets to patient and clever investigation. The merger between Andromeda and the Milky Way, that inevitable collision billions of years in the future, represents a natural experiment we can predict and prepare for, even though no humans as we currently exist will be around to witness it. We can simulate the collision using computers, modeling the gravitational interactions, predicting how stars will be redistributed, calculating when and how the central black holes will merge. These simulations have improved dramatically over the past few decades as computing power has increased and numerical techniques have become more sophisticated. Modern simulations can track billions of particles representing stars and dark matter, can model the hydrodynamics of gas clouds, can incorporate star formation and stellar feedback and black hole accretion. They produce movies showing the collision from various perspectives, time-lapse sequences compressing billions of years into minutes of video. Watching these simulations is mesmerizing, seeing two majestic spiral galaxies approach each other, begin to interact, distort and disrupt each other's structures, merge into a chaotic system that gradually settles into a new elliptical galaxy. But are the simulations accurate? Do they correctly predict what will actually happen, or are they just pretty pictures that miss important physics? This is harder to answer than you might think. We can't run the actual experiment, can't wait 4 billion years to see if our predictions were correct. What we can do is simulate past mergers, galaxies we observe in various stages of collision, and see if our models match what we observe. And mostly they do, which gives us confidence that we understand the basic physics, that our simulations are capturing the essential processes even if they miss some details. The details matter, though, especially if you care about specific outcomes rather than general trends. Will Earth survive the collision? Almost certainly not in any recognizable form. Not because of direct impacts, which remain unlikely given the vast spaces between stars, but because the Sun will have already evolved into a red giant by the time the galaxies merge. Our planet will have been engulfed or at least scorched sterile long before Andromeda arrives. So the question is really about where the Sun, if it still exists as a white dwarf remnant, will end up in the merged galaxy. Will it be flung into the halo, ejected entirely, or settle into some orbit within the new system? Simulations suggest all three outcomes are possible for different stars, depending on their locations and velocities at various stages of the merger. Some stars will be thrown out of the merged galaxy entirely, becoming intergalactic wanderers drifting through the void. Others will remain bound but in highly elliptical orbits that take them far from the galactic center. Still others will settle into relatively normal orbits in the new galaxy's structure. It's impossible to predict the fate of any specific star, including the Sun, because the outcome depends sensitively on details of the collision that we can't know in advance. This is chaotic dynamics in action, sensitive dependence on initial conditions, the butterfly effect writ large on galactic scales. Tiny differences in initial positions or velocities amplify over time until they produce completely different outcomes. We can predict the statistical properties of the merger, can say with confidence that an elliptical galaxy will form and that both black holes will eventually merge. But we can't predict the fate of individual stars because the system is fundamentally chaotic, because small uncertainties grow exponentially over time. This limitation frustrates some people, who want definitive answers to specific questions. But it's a fundamental feature of complex dynamical systems, not a failure of our understanding or our simulation techniques. Some things are inherently unpredictable, not because we lack information but because the systems themselves amplify tiny uncertainties until prediction becomes impossible. Weather is like this on Earth, predictable in the short term but fundamentally unpredictable more than a week or two in advance because the atmosphere is a chaotic system where small changes cascade into large effects. Galaxy collisions are even more extreme, playing out over billions of years, involving trillions of interacting objects, governed by gravity which creates the orbital resonances and instabilities that lead to chaos. We can predict the broad outlines but not the fine details, can say what kind of galaxy will result but not where any specific star will end up. And perhaps that's appropriate. Perhaps some aspects of the universe should remain uncertain, should resist our attempts at complete prediction and control. Perhaps deterministic chaos is nature's way of keeping us humble, reminding us that knowledge has limits, that not everything can be calculated in advance no matter how powerful our computers or sophisticated our theories. But let's return to Andromeda itself, to features we haven't fully explored, to aspects of this galaxy that deserve attention. We've focused primarily on the center, on the supermassive black hole and the dense stellar population surrounding it. But Andromeda extends far beyond its visible disk, far beyond the spiral arms that show up in photographs. The dark matter halo we've mentioned extends to hundreds of thousands of light-years from the galactic center, perhaps even millions of light-years, gradually fading into the general dark matter distribution of the local group. How do we know this? We can't see dark matter directly, can't take pictures of the halo or observe it with any telescope. But we can infer its presence and measure its extent through several methods. One is the rotation curve we've already discussed, the fact that stars in the outer reaches of galaxies move faster than they should if only visible matter existed. But that only tells us about dark matter within the visible disk. To probe the halo further out, we need different techniques. Satellite galaxies provide one method. These small galaxies orbiting Andromeda feel the pull of its dark matter halo, and their motions reflect the halo's mass and extent. By measuring the velocities and positions of multiple satellites, we can map out the gravitational potential, can reconstruct the dark matter distribution. It's like inferring the shape of a valley by watching how water flows through it, using observable effects to deduce invisible causes. Gravitational lensing offers another approach. When light from distant galaxies passes near Andromeda, its path bends slightly due to Andromeda's gravity, both from normal matter and from dark matter. This bending distorts the images of background galaxies, stretching them slightly in predictable ways. By measuring these distortions for many background galaxies, we can map the total mass distribution including dark matter. It's a powerful technique, one that's revealed dark matter distributions in galaxy clusters and individual galaxies, confirming that dark matter halos extend much further than visible matter. What emerges from these studies is a picture of Andromeda as a relatively small visible structure embedded in a much larger dark matter halo. The stars and gas we can see, that make up the beautiful spiral galaxy in our photographs, represent just a small fraction of Andromeda's total mass, a luminous core sitting at the center of a vast dark structure. It's like finding out that an iceberg you thought you understood is actually 10 times larger than the visible portion above water, that most of its mass and volume lies hidden beneath the surface. This is true for all galaxies, not just Andromeda. Every galaxy we can see is surrounded by a dark matter halo that outweighs the visible matter by factors of 10 or more. Galaxies are primarily dark matter structures, with normal matter condensing in the central regions where it can cool and form stars. We see the bright centers and mistake them for the whole galaxy, but really we're seeing just a small part of much larger and more massive systems. Does this change our understanding of what galaxies are? Perhaps. Perhaps we should think of them primarily as dark matter halos with some normal matter mixed in, rather than as collections of stars with some dark matter around them. The dark matter came first, collapsed first under gravity, created the potential wells into which normal matter fell. Stars formed later, after the dark matter structure was already in place. In this view, galaxies are fundamentally dark matter phenomena, with the visible components being relatively minor additions that happen to be the only parts we can directly observe. But dark matter's influence extends beyond just providing gravitational scaffolding for galaxy formation. It also affects how galaxies interact with each other, how they merge, how they evolve over cosmic time. When two dark matter halos approach each other, they begin to interact gravitationally long before the visible galaxies collide. The halos deform each other, transfer energy and angular momentum, create tidal forces that can trigger star formation or strip gas from the galaxies. The merger of dark matter halos is actually the primary event, with the merger of visible galaxies being a consequence of that larger process. Think of it this way: we see two galaxies approaching each other, preparing to collide. What we're really seeing is two dark matter halos, each containing a visible galaxy, beginning to merge. The halos interact first, over larger scales and longer timescales. They pull on each other, distort each other's shapes, exchange matter through tidal streams. The visible galaxies are along for the ride, responding to the gravitational environment created by the dark matter. They collide and merge because the dark matter halos are merging, not as an independent process. This perspective emphasizes how much of the universe's structure and evolution is driven by components we can't directly observe. Dark matter shapes cosmic structure on the largest scales, determines which regions of space will eventually form galaxy clusters and which will remain relatively empty. Dark energy drives the universe's accelerating expansion, determining its ultimate fate. Together, these invisible components control cosmic evolution, while normal matter, the stuff we can see and touch and study directly, plays a relatively minor role in the grand scheme. It's disorienting in some ways, this recognition that we're made of the minority component, that the universe is primarily something we can't see. But it's also exciting, a reminder that major discoveries remain to be made, that we don't have all the answers, that the universe retains its capacity to surprise us. Every observation that constrains dark matter's properties, every theoretical development that suggests what it might be, every experiment searching for dark matter particles, all of these contribute to solving one of science's greatest mysteries. And Andromeda is central to this quest, both as an object of study in its own right and as a test case for our understanding of galaxy formation and dark matter's role in that process. By comparing Andromeda's properties to our models of how galaxies form in a dark matter-dominated universe, we test those models, refine them, identify where they succeed and where they need improvement. Andromeda isn't just a beautiful spiral galaxy. It's a laboratory, a natural experiment, a piece of evidence in the grand investigation of cosmic structure and evolution. Consider the satellite galaxies orbiting Andromeda, those dwarf systems we've mentioned several times. Theory predicts they should exist, that dark matter halos should be hierarchical, containing smaller halos within them, each of which can host a small galaxy. Early simulations predicted Andromeda should have hundreds of satellites, far more than the few dozen we actually observe. This created what's known as the missing satellites problem, a discrepancy between theory and observation that had to be explained. Several solutions have been proposed. Perhaps most satellites are too small and faint for us to detect, just below the threshold of current observations. Perhaps feedback from star formation, particularly the effects of supernova explosions, prevents gas from cooling and forming stars in the smallest halos, leaving them dark and invisible. Perhaps dark matter isn't cold after all, isn't made of particles that move slowly compared to light speed, but has some residual velocity that smooths out structure on small scales and prevents the smallest halos from forming. Each of these possibilities has implications beyond just Andromeda's satellite count. They affect our understanding of dark matter's nature, of how star formation works in small systems, of what we should expect to find in future surveys with more sensitive instruments. The missing satellites problem isn't just a puzzle about Andromeda. It's a window into fundamental physics, a clue that might help us understand dark matter better or identify flaws in our current models of structure formation. Recent observations with more sensitive instruments have found additional satellites around Andromeda, dozens of extremely faint dwarf galaxies that were invisible to earlier surveys. This partially resolves the missing satellites problem, shows that some of the predicted satellites do exist but were just too faint to see. But discrepancies remain, and the question isn't fully settled. We continue to survey the regions around Andromeda, looking for even fainter satellites, mapping out the full population of dwarf galaxies that orbit the larger system. Each new satellite discovered adds data, helps constrain models, provides another test of our theories. It's painstaking work, scanning enormous areas of sky looking for tiny overdensities of faint stars, confirming that these overdensities are real structures rather than statistical fluctuations, measuring their properties and adding them to the catalog. But this is how science advances, through careful observation and patient accumulation of data, through asking specific questions and designing observations to answer them, through building up comprehensive pictures one data point at a time. And sometimes we find surprises. Sometimes observations don't match expectations, revealing something unexpected about how galaxies work or how structure forms. The Great Plain of Andromeda is one such surprise, a planar distribution of satellite galaxies that seems too organized to be random. About half of Andromeda's satellites orbit in a thin disk rather than being randomly distributed throughout the halo as simulations predict. This plane is rotating, suggesting the satellites share some common history, perhaps formed together or were captured during a single ancient merger event. The existence of this plane challenges our understanding of how satellite systems form and evolve. Random accretion of satellites over cosmic time should produce a roughly spherical distribution, not a thin plane. Several explanations have been proposed, from fine-tuned initial conditions to modifications of gravity on large scales, but none is entirely satisfying. It's possible the plane is a temporary configuration, that given enough time the satellites will be scattered into a more spherical distribution. Or it's possible we're missing something fundamental about how structure forms in the outskirts of large galaxies. The Milky Way has a similar plane of satellites, suggesting this might be a general feature rather than a peculiarity of Andromeda. But why would both galaxies independently develop planar satellite systems if such configurations are rare or unstable? The question remains open, a puzzle waiting to be solved, a hint that our models might be incomplete or that we need to consider processes we've overlooked. This is the reality of frontier science, of investigation at the edge of knowledge. Not everything fits neatly into existing frameworks. Anomalies appear, observations conflict with predictions, mysteries emerge. Some turn out to be instrumental errors or statistical flukes, resolved when better data becomes available. Others reveal genuine gaps in our understanding, pointing toward new physics or new phenomena. Distinguishing between these possibilities requires careful analysis, independent confirmation, theoretical investigation of alternative explanations. The plane of satellites might ultimately prove to be a minor curiosity, easily explained within our current framework once we better understand satellite accretion history. Or it might be a major clue, indicating that something fundamental in our models needs revision. We can't know yet. We need more observations, better simulations, deeper theoretical understanding. The investigation continues, as it always does, driven by curiosity and careful attention to phenomena that don't quite fit our expectations. And this brings us to a broader question about Andromeda and galaxies in general: how much diversity exists in the galactic population? Are all spiral galaxies basically the same, differing only in size and mass and minor details? Or is there significant variation, different formation histories producing different outcomes, each galaxy unique in important ways? The answer appears to be both. On one hand, galaxies show remarkable regularities. Spiral galaxies have similar structures, elliptical galaxies follow predictable scaling relations. The relationship between black hole mass and galaxy properties holds across enormous ranges. These regularities suggest underlying physical processes that operate similarly in all galaxies. Universal mechanisms that shape galactic evolution regardless of specific details. On the other hand, every galaxy has a unique history, a specific sequence of mergers and interactions and environmental influences that produced its current state. Andromeda isn't identical to other spiral galaxies. Its satellite system differs from the Milky Way's. Its star formation history has its own particular timeline. The details matter, the specific events that shaped each galaxy's evolution leave marks, create distinctions, generate diversity within the overall patterns. This is true throughout nature, this interplay between universal laws and particular histories. All stars follow similar life cycles, but each star has unique properties depending on its mass and composition and age. All planets form through accretion, but each planet develops its own characteristics depending on where it formed and what materials were available. Universal processes operating on unique initial conditions produce both pattern and diversity, both predictability and surprise. Andromeda illustrates this beautifully. It's recognizably a spiral galaxy, clearly belonging to that class of objects, sharing fundamental properties with other spirals. But it's also distinct, individual, shaped by its particular history in ways that make it different from every other galaxy. Understanding Andromeda requires both understanding the general principles that govern all galaxies and appreciating the specific details that make this galaxy unique. And that history includes violence, includes collisions and mergers and the cannibalization of smaller systems. We've seen evidence of this in the stellar streams, in the disturbed morphology of the central regions, in the complex structure of the halo. Andromeda didn't form in isolation, didn't evolve peacefully over billions of years without interactions. It grew through cosmic violence, consuming neighbors, surviving collisions, building up mass by incorporating matter from other systems. This is how all large galaxies form, through hierarchical merging, smaller systems combining to form larger ones over cosmic time. The early universe contained many small galaxies, proto-galaxies really, forming from the first generations of stars. These merged repeatedly, building up larger systems, gradually assembling the massive galaxies we see today. Every large galaxy has a merger tree, a branching diagram showing which smaller systems combined and when to produce the current galaxy. Reconstructing these merger trees is challenging but possible, using a combination of observations and simulations. Stellar populations with different ages and compositions mark different merger events. Streams and shells of stars in the halo reveal tidally disrupted satellites. Computer simulations can model how structure grows through hierarchical merging, predicting what we should see and comparing with observations. Slowly, painstakingly, we're piecing together the histories of individual galaxies, reconstructing their formation from scattered evidence. Andromeda's merger tree is complex, involving numerous minor mergers and at least one or two major ones. Evidence suggests a significant merger event about 2 billion years ago, when a galaxy perhaps a quarter of Andromeda's mass collided with and was absorbed by the larger system. This event disturbed Andromeda's structure, created some of the stellar streams we observe, possibly influenced the galaxy's current morphology. Other, smaller mergers occurred throughout Andromeda's history, each adding mass, each leaving traces, each contributing to the galaxy we observe today. And the biggest merger of all is still to come, the collision with the Milky Way that will create an entirely new system from two large spirals. This will be Andromeda's last merger as a distinct entity, the final chapter in its independent existence. After that, Andromeda will cease to be, will have merged into something new, something different, something that combines the properties of both progenitors into a single large elliptical galaxy. Is this tragic or beautiful? The end of one galaxy and the birth of another. Death and renewal. Destruction and creation. Perhaps such human concepts don't apply to galaxies, don't map onto phenomena so vast and slow that no observer could perceive them as events. Galaxies don't live and die in any biological sense, don't experience birth and death as conscious beings do. They simply evolve, transform, change from one configuration to another according to physical laws that care nothing for preservation or destruction, that simply describe how matter behaves under various conditions. Yet there's something poignant about it nonetheless, something that resonates with human experiences of change and loss and transformation. We assign meaning to cosmic events even when those events occurred long before humans existed or will occur long after we're gone. We see stories in the evolution of galaxies, narratives of growth and collision and merger. We anthropomorphize the cosmos, project our concerns and emotions onto phenomena that operate according to mindless physical processes. Is this wrong? Is it inappropriate to view galaxies as having stories, to speak of their histories and futures in narrative terms? Perhaps, if we confuse metaphor with reality, if we forget that the human interpretive framework we're imposing doesn't reflect any actual experience or intention on the galaxy's part. But perhaps it's also unavoidable, perhaps even necessary. We're narrative creatures, storytelling beings who make sense of the world through stories. Forcing ourselves to speak only in cold equations and technical descriptions might be more accurate in some sense, but it risks losing the wonder, the emotional connection, the sense of meaning we find in contemplating the cosmos. So yes, Andromeda will die when it merges with the Milky Way, even though galaxies don't literally die. The structure we currently recognize as Andromeda, the particular arrangement of stars and gas and dark matter that we've identified as a distinct entity, will be disrupted and mixed into a larger system. The name Andromeda will persist only as a historical reference, a label for something that used to exist. And something new will emerge, a galaxy unlike either progenitor, larger and more massive, with its own structure and dynamics. This process has happened countless times throughout cosmic history, will continue happening as long as gravity operates and galaxies interact. It's how structure grows, how the universe organizes matter on increasingly large scales. Individual galaxies are temporary configurations, existing for billions of years but ultimately impermanent, eventually merging into larger systems or being torn apart by tidal forces. Only the matter itself persists, continuously recycling through different structures, different configurations, different forms. And what of consciousness, of observation, of the beings who might exist in Andromeda or will exist in the future merged galaxy? Do they experience these cosmic transformations? Do they care about the names we assign to galactic structures? Do they develop their own astronomy, their own understanding of cosmic evolution? These questions veer into speculation, into fiction almost, but they're worth considering. If life exists in Andromeda, and the statistics suggest it should if life is at all common in the universe, then beings there might look out at the Milky Way the way we look at Andromeda. They might identify it as their closest large galactic neighbor. They might calculate that a collision is inevitable. They might wonder what will happen to their world, their civilization, their species when the galaxies merge. Would they try to prevent the merger? Could they? Almost certainly not. The energies involved, the scales of space and time, dwarf anything even an advanced civilization could influence. Moving entire galaxies is beyond anything we can imagine being technologically possible, requires energy scales that approach cosmic limits. No, the merger would proceed regardless, indifferent to the wishes or concerns of any inhabitants. But perhaps they could migrate, could move their civilization to a safer location before the chaos of merger disrupts their home system. Perhaps by the time galaxies collide. For billion years from now, any civilizations that survive that long will have expanded beyond single planets or solar systems, will inhabit numerous worlds scattered across their galaxy or beyond. Perhaps they'll view the merger with scientific interest rather than existential dread, as an opportunity to study cosmic processes up close rather than as a threat to survival. Or perhaps they'll be long extinct, as species seem to be in the long run, replaced by successors or evolved into something unrecognizable or simply gone, victims of catastrophe or natural processes or the simple fact that nothing biological lasts forever. The timescales of galactic evolution are so vast that biological species, which typically exist for millions of years before going extinct or evolving into something else, barely flicker into existence and vanish again. Civilizations might last longer if they develop technologies for preservation and expansion, but even that's uncertain. We have no examples other than our own, and we've barely lasted a few thousand years of recorded history. The likelihood that any specific civilization survives for billions of years approaches zero. But the likelihood that some civilizations exist somewhere during that time might be high, if life is common. So perhaps the merger of Andromeda and the Milky Way will be observed by someone, some species or intelligence that develops in one galaxy or the other over the next few billion years, witnesses the collision, studies it, records it for posterity. Or perhaps not. Perhaps the local group is barren, perhaps Earth is the only place in these two galaxies where consciousness has emerged, and when we're gone, there will be no observers left to witness the greatest astronomical event in our corner of the universe. These are unanswerable questions, at least with current knowledge. We can't detect life on planets in other solar systems, can barely detect the planets themselves. We've found thousands of exoplanets through various techniques, confirmed that planetary systems are common, demonstrated that Earth-like worlds probably exist in large numbers. But we can't yet study their atmospheres in detail, can't search for biosignatures, can't determine if any harbor life. That will change. Next-generation telescopes, particularly large space-based instruments that can block star light and directly image planets, will enable atmospheric spectroscopy, will allow us to search for oxygen and methane and other gases that might indicate biological activity. We'll be able to determine if Earth-like planets have Earth-like atmospheres, if they show signs of life, if the universe is teeming with biology or if Earth is a rare oasis in a barren cosmos. And then there's the search for technological signatures, signs of advanced civilizations that might be detectable across interstellar or even intergalactic distances. Radio signals, laser communications, waste heat from massive engineering projects, modifications to stars or planets that reveal intelligent activity. We've been conducting SETI, the search for extraterrestrial intelligence, for decades now, listening for radio signals that might indicate someone's trying to communicate or that we're picking up leaked transmissions from alien civilizations. So far, silence. No confirmed signals. No evidence of anyone out there. This could mean many things. Perhaps life is rare, perhaps intelligence is rare, perhaps civilizations don't last long enough to be detectable. Perhaps they're using communication technologies we haven't thought of, or they're deliberately staying quiet, or we're looking in the wrong places at the wrong times with the wrong techniques. Perhaps the universe is full of life and intelligence, but the distances are so vast and the number of possible places to look so enormous that we simply haven't stumbled across anyone yet. The Drake equation attempts to quantify this, to break down the question of how many communicating civilizations exist in the galaxy into separate factors: rate of star formation, fraction of stars with planets, number of habitable planets per system, fraction where life develops, fraction where life becomes intelligent, fraction that develops detectable technology, length of time they remain detectable. Multiply all these factors together, and you get an estimate of how many civilizations exist at any given time. But we don't know most of these numbers. We can estimate star formation rates, and we're starting to understand planetary occurrence, but the later factors, the biological and sociological ones, are completely uncertain. The fraction of habitable planets where life actually develops might be close to 1, or it might be astronomically small. We have one example, Earth, and you can't determine probability distributions from a sample size of 1. So the Drake equation, while conceptually useful, doesn't actually answer the question. It organizes our ignorance, shows us what we need to know, but doesn't provide answers. We're left with uncertainty, with the recognition that the universe might be teeming with life or might be essentially barren, and we can't currently distinguish between these possibilities. What would it mean for Andromeda specifically? If life is common, then surely some exists there, distributed among the galaxy's trillion stars and countless planets. If intelligence emerges frequently, then perhaps civilizations exist in Andromeda right now, looking back at the Milky Way, possibly even detecting us, wondering if anyone else is out there. Perhaps they're sending signals we haven't detected yet. Perhaps they've sent probes that are still in transit across the intergalactic void. Perhaps they went through a SETI phase like we're in, searching for others, finding silence or finding signals, either way learning something about their place in the cosmos. Or perhaps Andromeda is dead, lifeless, empty except for the physical processes that govern stars and gas and planets. Perhaps in all those trillions of stars, across billions of years of history, life never emerged, or emerged but remained simple, or developed intelligence but destroyed itself, or exists but hasn't developed detectable technology. Perhaps we're looking at a massive galaxy containing more stars than our minds can comprehend, and it's completely devoid of consciousness, of awareness, of anything that could be called life in any meaningful sense. Both possibilities are profound. Both challenge our understanding of our place in the universe. If life is common, we're not alone, we're part of a cosmic community, one species among many that have achieved consciousness and sought to understand the universe. If life is rare, we're lonely, precious, perhaps the only beings in our corner of the universe capable of asking these questions, of studying galaxies and black holes and the ultimate fate of the cosmos. Which is correct? We don't know. And this uncertainty, this fundamental ignorance about one of the most profound questions we can ask, should humble us. We've learned so much about the physical universe, about galaxies and stars and cosmic evolution. But we know almost nothing about biology beyond Earth, about whether life is common or rare, about what forms it might take, about whether intelligence and consciousness are inevitable products of evolution or rare accidents that might occur only once in a galaxy or once in the entire universe. The journey to the center of Andromeda, then, is incomplete without considering this question. What are we looking at when we observe this galaxy? Are we seeing a physical structure, beautiful and complex but ultimately lifeless? Or are we seeing a living galaxy in some sense, containing countless worlds where biology has gained a foothold, where evolution has proceeded for billions of years, where consciousness might have emerged many times in many forms? The question remains unanswered, perhaps will remain unanswered for generations. But it colors our perception, adds layers of meaning to our observations, transforms Andromeda from merely an astronomical object into a possibility, a question mark, a reminder that we don't know everything, that the universe retains its capacity to surprise us in the most fundamental ways. And perhaps this is fitting. Perhaps the journey to Andromeda's center should end not with certainty but with questions. Not with complete understanding but with recognition of what we don't know. Science advances by asking questions, by identifying gaps in knowledge, by maintaining curiosity about phenomena we don't yet understand. Definitive answers are rare and often temporary, subject to revision when new evidence emerges. Questions persist, driving investigation, motivating observation, pushing us to learn more. So we stand, metaphorically, at the center of Andromeda, having journeyed through its structure, contemplated its supermassive black hole, considered its dark matter halo and stellar populations and merger history. We've learned about galaxy formation and evolution, about black holes and dark matter and the large-scale structure of the universe. We've touched on questions of consciousness and life and meaning, on what it means to be observers in this vast cosmos, on how we fit into the grand sweep of cosmic history. And we recognize, in the end, that the journey is never complete, that understanding is always partial, that the universe is larger and stranger and more wonderful than any finite mind can fully comprehend. Andromeda waits in the night sky, patient and eternal on human timescales, ready to reveal its secrets to anyone willing to look carefully, to think deeply, to ask questions and seek answers with patience and determination. This is the legacy we inherit from centuries of astronomical observation, from generations of scientists who looked up and wondered and investigated and gradually built our current understanding. And it's the legacy we pass forward, to future generations who will continue the investigation, who will make discoveries we can't imagine, who will answer questions we haven't thought to ask and ask new questions we haven't conceived of. The center of Andromeda holds mysteries still, secrets waiting to be discovered, phenomena we haven't yet detected or understood. The supermassive black hole continues its silent reign, warping spacetime, holding the galaxy together through invisible gravitational forces. The dark matter halo extends into the intergalactic void, connecting Andromeda to the larger cosmic web. Stars are born and die, planets form and evolve, matter cycles through different configurations in an endless cosmic dance. And 2.5 million light-years away, on a small planet orbiting an average star, conscious beings look outward and wonder, asking questions about their place in the universe, seeking understanding of phenomena vastly larger and older than themselves. This is remarkable. This is extraordinary. This is what it means to be human in a cosmos that inspires wonder and defies complete comprehension. The journey to Andromeda's center is ultimately a mirror, reflecting back our own capacity for understanding, our drive to explore, our refusal to accept ignorance when knowledge is possible. We see ourselves in that distant galaxy, recognize our connection to cosmic processes that shaped both Andromeda and the Milky Way, understand that we're part of something vastly larger than ourselves. And perhaps this is the final revelation, the ultimate truth we discover in our journey, that we belong to the universe in the most literal sense, that we're not separate observers but participants, that studying the cosmos is studying ourselves. The atoms in our bodies were forged in stellar cores. The patterns of thought in our brains reflect the organization of matter that emerges naturally from physical law. The wonder we feel contemplating galaxies is the universe wondering at itself through us. This perspective doesn't diminish our significance. If anything, it enhances it, reveals us as extraordinary phenomena in our own right, conscious beings capable of understanding the cosmos that created us. We're rare, perhaps vanishingly rare, possibly unique in our corner of the universe. And whether common or rare, we represent something profound, something that emerged naturally from cosmic evolution yet transcends mere physics and chemistry, adding layers of meaning and experience and understanding to the universe's vast complexity. So the journey to Andromeda's center ends where it began. With recognition of both knowledge and mystery, with appreciation for what we've learned and excitement about what remains to be discovered, with humility about our place in the cosmos and pride in what we've achieved. We've touched the heart of a distant galaxy through observation and calculation and imagination. We've comprehended phenomena billions of light years away and billions of years old. We've expanded human understanding incrementally, adding our small contributions to the accumulated knowledge that spans generations. And Andromeda waits still, patient and unchanged by our observation, continuing its ancient dance through space, preparing for its eventual merger with our galaxy, holding secrets we'll spend centuries uncovering. The supermassive black hole sits at its center, a cosmic enigma, a natural laboratory where physics reaches extremes we cannot replicate, where spacetime itself warps into impossible configurations. This is where our journey ends, at the center of Andromeda, at the edge of a black hole, at the boundary between known and unknown. We've come as far as current understanding allows, pushed against the limits of knowledge, glimpsed phenomena that challenge our deepest theories. And we recognize that this isn't an ending but a beginning, that every answer reveals new questions, that the investigation continues as long as curious minds exist to pursue it. The universe spreads out around us, infinite in its complexity, eternal in its evolution, magnificent in its capacity to surprise and inspire. Andromeda is one galaxy among billions, one structure in the vast cosmic web, one temporary configuration of matter that will eventually merge and transform into something new. But it's our galaxy to study, our neighbor in the cosmos, our window into processes that operate throughout the universe. And so we return, having journeyed in imagination to places we cannot physically reach, having touched through understanding phenomena we cannot directly experience. We carry with us new knowledge, new questions, new appreciation for the universe's complexity and our ability to comprehend it. The journey to Andromeda's center changes us, expands our perspective, reminds us of our place in something vastly larger than ourselves. This is the power of science, the gift of understanding, the triumph of human curiosity over cosmic indifference. We looked up at a patch of light in the night sky and discovered a universe. We measured and calculated and theorized our way to comprehension. We transformed ignorance into knowledge, darkness into light, mystery into understanding. The journey continues. Always. Forever. As long as there are minds to wonder and eyes to observe and hearts moved by the beauty of the cosmos. Andromeda waits in the darkness, a destination both reached and forever distant, comprehended yet still mysterious, known yet still capable of surprising us. And we, having journeyed to its center, return transformed by the experience, carrying new understanding, new questions, new wonder at the magnificent universe we inhabit and are privileged to investigate. This is the meaning of the journey. Not arrival but exploration. Not answers but questions. Not certainty but wonder. Not ending but continuation of the endless human quest to understand the cosmos and our place within it. Andromeda waits. The journey continues. The universe reveals its secrets slowly, patiently, to those willing to look carefully and think deeply and maintain their sense of wonder at the cosmic drama playing out across billions of years and trillions of miles of space. And we, impossibly small yet impossibly significant, continue our investigation, adding our voices to the centuries-long conversation about the nature of reality, contributing our observations to the growing body of human knowledge, participating in the grand project of understanding that defines us as a species and gives meaning to our brief existence in this vast, ancient, magnificent universe.